faculty are collaborating with foreign experts in their field. This is one of the example. And so many of the faculty, I mean, if you see most of our faculty profiles, we are working in almost all areas of mathematics, algebra, analysis, mathematical application, statistics, and computing related. And we have three programs: PhD, MSc, and BTech. And one good news is that many of our students who completed PhD here, they are working as assistant professors in most of the reputed institutes in India, like ICERs, IITs, NITs, and central universities. And coming to our MSc program, this is also one of the successful program. And there are two branches in that. One is mathematics, and other one is mathematics and computing. Most of our students are placed in most very reputed companies, and even many of the students are working in as PhD students in India and abroad. And coming to BTech program, it is one of the successful program started. I think we are third institute starting that program in India. And if you see our record, it is 100% placement from last many years from the beginning of the program. So if you have anybody who want to join in the department, your relatives or friends, you please tell about our department. And coming to institute, you see you have a lot of good infrastructure in the institute. You can go around the campus. Library is very nice in the institute. We can, whenever you have some free time, you can go and spend some time in library. And coming to the program, this is the second program in our department. So we conducted one program in 2013 or 14 on function analysis, and this is the second program after a lot of gap. And recently, only last 1 year back, we shifted our department. Earlier, we were scattered around in the institute in different departments. So now we have our own building. And after shifting to the new building, we are witnessing many successful programs like one of these. And earlier, Professor Rajesh conducted AFS program, and one more professor conducted workshop on function analysis. So we are very actively engaging most of the research and teaching. So you can utilize this opportunity and interact with these two experts, and you can get maximum benefit. And we were discussing last time with
So I will briefly tell about his profile and then we will go on to the lectures. Okay. So he did his bachelor's from University of Bucharest, Romania. Then he did his master's and PhD from Queen's University at Kingston, Ontario, Canada. Then he was a postdoc at University of California, San Diego, with Franchum. Then he did his postdoc in University of Then in 2009, he joined the University of California. So right now he's a professor in the Department of Mathematical Sciences in University of California. Yeah, with this brief introduction, I read it's a way to start.
Okay. So I have to go in the camera. Yeah.
So thank you for the introduction. I'm very honored and very happy to be here in India. This is the first time I have been in this country, and I've had a wonderful time. So today, I don't know much about your background, and so we'll have a course for 1 week on spectral graph theory. I'll try to set up the foundations in the first lecture today, and we'll progress to applications and to interesting problems throughout the week. So the first day may be a little bit known to some of you because we'll go over some basic stuff in linear algebra and some basic stuff in graph theory. But hopefully you'll find something interesting in what
we discuss today. Okay. So let me get my stuff from here. Okay, so I'll write something here. I'm going to use the Blackboard for most of the talk, but this is a fancy screen, so I don't get to use it that much, so why not? We used it yesterday, but now hopefully I remember how to do these things. Let's see. Okay, so the course is about spectral graph theory. So what is spectral graph theory? Well, you have in mathematics, you have many areas. So one of them will be graph theory, combinatorics, and all that, discrete structures. And you have, on the other side, you have linear algebra, where you have matrices, eigenvalues, eigenvectors, and all that. So spectral graph theory, what it does, it studies the connections between these two areas. So maybe when you're young and you're undergraduate, I know that it happens to some students that I've taught. You believe that mathematics is a bunch of separate islands that don't talk to each other and so on. Well, you know, hopefully by now, the more you learn about mathematics, you realize that many things connect to each other. And so it's not a surprise here that you have a rich interaction between graph theory and discrete structures, like I mentioned, and linear algebra. So in this type of problems, you can, you know, if you have a graph, you know something about its structure, something of its properties, the question will be how does that reflect in terms of linear algebra properties, and vice versa. If you know something about the linear algebraic properties of the graph, how does it reflect in terms of the structure? So in this course, I will give you examples where these things happen, and there are many situations in which linear algebra provides a solution to like graph theoretic problem, combinatorics problem that we wouldn't be able to get in any other way. So it's an interesting area. There's a okay, so that's the key principle about the course that I'll try to convince you this week. Now I will start. Do we have chalk? No, sorry. Okay. So today, like I said, we'll talk about linear algebra. And I have a colleague at University of Delaware who told me once that you can never know enough linear algebra. So whatever you think you know about linear algebra, maybe there's more to learn. Like I said, some of these things maybe you already know, but I want to start here just to kind of lay a foundation about what we're going to talk for the rest of the week. And the key idea here, or tool in spectral graph theory is the spectral decomposition theorem. And because I will talk about undirected graphs, the matrices that we'll talk about in this this week will be real and symmetric. So this is what we'll talk about. So this is the key thing. Everything that will derive, like the results that we'll discuss this week, they will come from, like, at the bottom of it. Everything is from spectral decomposition theorem, and we'll talk about it in a second. I'll tell you a little bit about it. And that explains, for example, maybe some of you are more advanced in this area, and maybe you have looked into, how do you so let me put here some star. How does one study spectral, maybe hypergraph theory, or spectral directed graph theory. These are just names that I made up right now. So you see, like, in attempting to generalize the results from spectral graph theory to other realms, like hypergraph theory, where edges have more than just two vertices, or directed graphs, where just because you have something from x to y doesn't mean that you have something from y to x. This is the main. This is the main block that one has to overcome, and also that's the approach that people have taken in some situations. Maybe I'll talk about it towards the end of the class. But for example, if you think about spectral directed graph theory, like if you have directed graphs, the matrices that, if you associate matrices to these directed graphs in the way similar to the way you would associate adjacency matrices, those matrices are not going to be symmetric. And so that puts a stop very quickly into anything that you try to develop. And that's why in this area, people have looked at something more general than real and symmetric, which are called Hermitian matrices. So that's why today, when I will tell you about the real and symmetric matrices, I will give you I'll give you two ways of looking at it. One, I will give you a proof of the spectral decomposition theorem, which is just for the case of real and symmetric matrices. And then I'll put that into a more general context. There are several spectral decomposition theorems in linear algebra for something called Hermitian matrices, or for normal matrices. And those are the approaches that people have taken when trying to extend some of the work from spectral graph theory to these new realms. Okay, so this is just some introductory stuff, just to kind of set up the main ideas. Okay. So, like I said, we're going to start at the beginning. So definition. So for me, let A be so we'll have a matrix, and I will denote here. You can have M and C, which are the set of all n by n matrices with entry complex. Or for now, let's do it like this. And you can be also over real. This is something that everybody knows. We say that lambda and u form an eigenpair for A if what has to happen? Well, lambda is a complex number, u is a vector which is not zero, and you have this equality that everybody knows. Okay, so that is what is an eigenpair, and in this case, lambda is an eigenvalue, and u is an eigenvector. Corresponding eigenvector of A corresponding or associated to lambda. Okay. Now, So eigenvalues, eigenvectors, I'm not going to go into a discussion. If you want to know like the deeper meanings of things, these days everybody is looking quickly for conceptual meaning and or things like that. You can look into, go on YouTube, but not now, later. And there are many like videos. 3 Blue, 1 Brown has very nice videos about the meaning of eigenvalue and eigenvector, and so on. So, okay. Now, again, in spectral graph theory, we're going to have graphs, we're going to have matrices. Matrices are going to have eigenvalues, eigenvectors, and we're going to try to study them this week. Okay, so this is basic stuff. Now, the first proposition is that every complex matrix has an eigenvalue. But let's do something else instead of, so I'll show you a proof that is from, I guess I forgot to give you the resources. So I'll put here some books for the things that I'll talk today. Now, in linear algebra, like I said, there are many facts, and sometimes you forget things. The book that I use to kind of, if I want to recall or if I want to find anything about matrices, is a book by Roger Horn and Charlie Johnson, which is called Matrix Analysis. So most of the proofs that I'll give you today in terms of linear algebra are taken from there. So I highly recommend it. It has a lot more than I'm showing you here. And you don't have to learn the whole linear algebra before you go do spectral graph theory, but it's useful for you to know some important spectral linear algebra before you do anything. Okay, so actually, let me give you the statement 2, the more general statement that will imply 1. So I wrote it here. For every vector which is non-zero, there is a polynomial g of x, again, let's say over complex, of degree. Okay, let me put here, before let A, I have my matrix here. So for every vector non-zero, there is a polynomial g of x of degree n minus 1 or less, such that GA times V is an eigenvector of A. Okay. So obviously, if you know 2, you know 1. So we'll just go quickly over 2. So we have V. Let's pick V not 0. And you've probably seen this argument before. It's a dimension argument, and that's how we do most things in linear algebra. So I'll write here on the side. If you have this V, you can look at V, you can look at AV, you can look at AN over V. So here you will have n plus 1 vectors, but they all live in an n-dimensional space, so they must be linearly independent. So there is a linear combination of them that gives you 0. Okay, and you can be a bit more clever about it, and you can say define M to be the least K such that V, AV, AKV are linearly dependent. So clearly such a K exists because n satisfy, but maybe you got lucky and you can, like there's a smaller exponent, so you can just take the smallest one of them. So now you basically just work out what that means. Okay, what does it mean they're linearly dependent? Therefore, there are some constants, let's say, did I put them here? Okay. A0, AM complex, not all zero, such that A0 V plus A1 AV plus AM AMV, it gives you the zero vector. Okay, and then you're almost done. So if you haven't finished copying and so on, and you want me to leave something on the board, just say something. Otherwise, I'm going to go ahead and just erase the board. So, yeah. Okay, so then you can define C of x to be this A0 plus A1x plus AMXM, and then from there we have that PA if it equals 0. Okay, and now you have to use something, and so what you have to use is this fact about polynomials with complex entries, that they have complex root. So then you can take that lambda be a root of p of x. So lambda is complex. So then what do we have? Then p of x is x minus lambda times g of x. And then you go from here, you go here, and you write what it means. So you can say this is 1, this is 2. What do you get? We get that a minus lambda I, this is n, ga of v equals 0. Okay. Do you see? So I factor p of x here is a like a non-determinant or a variable, x minus lambda g of x. If I factor the polynomial of the applied to the matrix, is going to be, instead of x minus lambda, you have a minus lambda identity, and then the g of x gets replaced by g of a. Okay. So this looks very much, I mean, here we didn't quite say it, but you've probably seen it before. AU equals lambda u, it's the same thing as a minus lambda identity is 0, which is the same thing as the kernel of a minus lambda I is not trivial. You have something that is not just 0 in there. You have more than 0. And now here you have a minus lambda I times something is 0. So here's the first I'll give you help, call it trick question of the day. Does this mean that GA of V is an eigenvector?
So that has to be non-zero.
That has to be non-zero. Very good. And that's where, in order to say that this is an eigenvector, which kind of I wanted to, that's the conclusion. So you kind of guess that that's what's going to happen. You have to argue that GA of V is non-zero. And GA of V, G, like what degree is G? M minus 1. And we agree that that's why this thing helped you at the beginning, that you take M to be the least k such that these are linearly independent. Essentially, this is the least degree of a polynomial, or if you calculate P of A and you multiply by V, you're going to get 0. And so here, this G of A has degree smaller. So you can say by the minimality of M, by the definition of M, the fact that it's the smallest such that we get that GA of V is not a zero vector. And now that's the conclusion. Therefore, GA of V is an eigenvector of A. Okay. So yeah, it's just a little bit different. So it's helpful to get used to kind of, you know, maybe undergraduates, whenever they see something about eigenvalues, okay, let's fire up the determinant and do characteristic polynomial. We'll do that, and you will see results about that. But you can do things without that. It's just a matter of like linearly dependence. Yes, question? Yes.
So here you're taking lambda to be a root of p of x, right?
Yes.
You actually know what p of x is. So you're assuming there's a root of that polynomial.
Yeah, because so that's what I said, that here I'm using this big thing about p of x being a polynomial of complex coefficients, and hidden in the background, we're not going to go all the way there. Yeah. So it's self-contained up to a point. Like yeah. So you're absolutely right. So yeah. Any other questions? No. Okay. All right. So yeah, this is important, and yeah, we'll use it for various things. Let me erase here. Now, for organization on my part, I just erased the result that I was going to ask you about it. So here I did something for every complex matrix has some eigenvector. Is it going to be true for any real matrix?
It depends on the base field you're asking. So you can put a real eigenvalue.
Yeah. That's the thing. That's a very good question. So if I look at the it depends on if I'm looking at real matrix. Am I looking for so the first thing, if I'm looking for real or complex eigenvalues, or if I'm looking for real and complex eigenvectors? Okay, so that's the question. Okay, so I have done this. Okay, so I'll leave you with this as an exercise for afternoon. Again, you can probably solve it in your sleep or something, but it's good to do it. So let A. So now the description of the real matrices that I asked a bit earlier. Assume that lambda u is an eigenpair of A, where lambda is complex number and u is also, I mean, I shouldn't write this, it's in the definition, but okay, so you have an eigenpair for, so A is real, you have an eigenpair lambda u, both of them are complex. How do you get yourself a real eigenvector? So if u equals, let me use this real part of u plus I imaginary part of u, then show that A times the real part of u, I'll talk about real part of u in a second, equals lambda times real part of u, and okay, so here you're going to have some complex entries, a1 plus ib1, an plus ibn. So then you break it down the way you would do it for complex numbers, a1 an plus I times b1 bn. So this is the real part of u, This is the imaginary part of you. Okay, so this is exercise, so I'm not going to solve it because exercises are meant to be solved by who? Okay, by students. So this is the first part, and second part, at least one. Well, so let me just add here, sorry. Real part of you and imaginary part of you. The key thing about them is that they're real vectors. And then in order, again, the same thing before, just because A times something equals lambda times something doesn't mean it's an eigenvector. You have to check it's non-zero. But this is what you will do. At least one of real of u and im of u is non-zero. Okay. You've probably done this in some undergraduate class, but yeah, it's good for you to do it. Okay, so that's exercise 1, so we can keep track of them. And then exercise 1 comes exercise 2. Again, we can talk about this in the afternoon. You guys have questions? Yeah, it's okay. Okay, so now, okay, so okay, so from over there, you kind of know where we're going. Okay, I want to, for a real matrix, I can say something about my my vectors being eigenvectors being being real. What do I want to tell you now? Okay. So let's do here. If A is symmetric and lambda u is an eigenpair of A with, again, lambda complex and u real, I can then see if you can, is it true that lambda is real? Okay. Okay, so this is, again, these are like at, let me erase here. These results form the foundation for the proof of what we're gonna do next. So I'll give you the, so I'll give you first the spectral decomposition theorem for real and symmetric matrices, because this is the only thing we'll need for this is the only thing we'll need for this week. And after we go through this proof, I'll give you another perspective of it, which is broader, which gives you, in which this theorem is a consequence of a bigger theorem called Schur's theorem, which this Schur's theorem is not something super complicated, but the Schur's theorem allows you to, with one stone, you can kill like many birds. So Schur's theorem is going to be a general theorem, and its consequences are going to be the spectral decomposition theorem for Hermitian, real and symmetric for normal matrices. So if you know, so but I think it's important for you to know both of these kind of approaches. And so let me state this for real and spectral, and sketch the proof. So let A be a matrix here, A symmetric. Then, okay, what do I want to say? What's the spectral decomposition theorem? Well, you can phrase it in different ways. So let me give you two different ways. Then one way that is going to be useful. This is one way that will apply it in many situations. Rn has an orthonormal basis formed by eigenvectors of A. So again, at the beginning you may, okay, what's the big deal? Well, the big deal is everything in this space is going to be written as a linear combination of eigenvectors of A. So everything in this space, I mean, the space is large. There are many things. There are many things that are not going to interest you. But everything that's going to like interest you that is a vector will be a linear combination by eigenvectors of A. So you can relate it to A. So that's going to be very important. And then if you take this orthonormal basis and you look at these vectors, because we look at the vectors usually as column vectors, and you put them in a matrix that is a column matrix, what you'll get is so this will be equivalent. There is a real and orthogonal matrix U. So orthogonal just means that U transpose U equals the, so the columns are form an orthonormal system, such that A equals, how did I write it here? AU, just 1 second. You can write U transpose AU equals D, where D is a diagonal matrix, where U transpose AU, or you can write it the other way if you want. Okay, so okay, so let's go through a quick proof of this, and then we can look at the extension also this morning. Okay, so the proof will go in a sequence of steps. Some steps will prove, some steps will leave it to you, some steps you know, so we'll go like that. What is the first part? The first part we already seen that, so we have let A be here. The first part is that the matrix A has a real, let's say, eigenpair lambda U, so lambda real U real. So based on what we mentioned earlier, you start with, okay, your matrix is going to have one real eigenvalue, one real eigenvector. And then we're going to do something to it and get so what we want to do is we want to get an orthonormal base is formed by the eigenvectors. That's what we're going to do. Okay. And here's the general procedure that again is very useful for you to know. If we have A, if you think about if you have an eigenvalue and you collect all the eigenvectors that correspond to that eigenvalue, together they form an eigenspace. And what's a consequence of that being an eigenspace? The consequence is if you take a vector from the eigenspace and you multiply by A, you stay in that eigenspace. The eigenvectors are even more special because if you take an eigenvector, you know exactly, you just scale the eigenvector and you multiply by adjacency matrix. Now, so in general, we have this notion. So let's say, let U be, I'll use this notation, be a subspace of Rn. We say that U is A invariant if U is contained, whenever you have a vector and you multiply it by A, you're not leaving the subspace. Okay, so that's a, so eigenspaces are going to be, you know, A invariant, but maybe they, you know, there could be more general things. So what's the result that we're going to prove here is that so A is real and symmetric if U is A invariant, then U perp. So this U perp is the collection of all vectors that are perpendicular to everything in U, is also A invariant. Proof 7. Okay, exercise 3. So in some situations when I put I get carried away with exercises, you can raise your hand and say, hey, can you prove it for us? But you know, so don't be shy about that. So okay. Okay, but here's the thing that we'll use. So you have 1, 2, you have now 3. If U is in Rn is A invariant, then, like I said, U could be many things, but what you will guarantee for sure is that U contains an eigenvector of A. So this one, maybe you've seen it, maybe you've not. I'm not going to leave this as an exercise, so we'll prove it right now. So, okay, so assume that U is an A invariant subspace of Rn. Okay, and let's say again, it's all about dimensions here. Denote K to be the dimension of U. Obviously, is the most n. Okay. So what we'll do, so this is a proof, you can find this proof in, so let me put another reference here. So another book, Chris Gottsill and Gordon Royal. Algebraic graph theory. Okay. So So now what we'll take a basis for U, and we're gonna put those vectors in a matrix. So let R be n times k matrix. So this is what I call tall matrix. So here you're going to have C1, C2, Ck columns. So it's a matrix whose columns form an orthonormal basis for U. Okay, so it's a base. And now what we'll do is we'll write down what it means that U is invariant in terms of this this matrix. Okay, so first let's write it a bit informally. You have A times R. So this is R. So it's A, and A meets this matrix. And again, it's good for you to know, like, there's a formula for multiplying matrices with the summations and so on. But there's a formula in which you can tell what happens if a matrix hits a column and so on. So here, the result will be a matrix, also a tall matrix, where the first row column will be AC1, and you'll have the columns ACK. I mean, surprise, surprise. A times C1, A times C2, A, so on. But now, what happens? So, each of these columns, where do they live? So, AC1, ACK live in U because U is A invariant. And now, if you live in U, who tells you how everything looks like in U? A basis. And we have a basis, C1, Ck. So each of them is going to be written as a linear combination of so let's just, I'll just do one example and then I'll write down so AC1 is going to be maybe alpha 1 C1 plus alpha K Ck. Okay? But how can you write this as a product of two matrices? You can write it as maybe this matrix C1 Ck, and you multiply it by alpha 1 alpha K, something like this. You see, think about C1 Ck as kind of like numbers, the way you do dot product, and you're going to be C1 Ck meets alpha 1 alpha K. Okay? So, well, what's going to happen? This happens for AC1. So AC1, you can write it as this matrix R times a vector. Well, it's going to happen for AC2. It's going to happen for everything, ACK. So these vectors, alpha 1, alpha K, you put them together in a matrix. And what you will get is, let me write it here. So from here, again, because so we're using both things because U is A invariant and C1 Ck is a basis of U, we get that. So let me do it kind of on the picture. A, which is a big matrix n by n, meets this tall matrix n, which is R by K. And now you see, like for each column C, I get a vector here, and I can put those vectors together, and I'm going to get something here of those vectors. Let's see how I call it. But no, I got it the other way around. Will be this tall matrix again, the R, which is n by k, times something small here, which is k by k, and I call this B. So I wanted to show you this because tomorrow we're going to talk about equitable partitions and interlacing and so on, and we'll see this picture again about A invariant subspaces and so on. And it's useful to kind of, it takes a little bit to get used to it, but it's not super complicated once you write it down and you think about it yourself. So is this clear? So we get that AR equals RB for some B matrix, which is MKR. So like I showed you here how AC1 is going to be C1 CK times alpha 1 alpha K. If you do AC2, it's going to be maybe beta 1 C1 plus beta K CK, which is again the same matrix of which is R times beta 1 beta K. So you just put these vectors of coefficients, you put them together and you get that. Okay? Okay. Okay. So, I mean, now kind of I tell you about some things, it's easy to lose track of what we're trying to prove. We're trying to prove that U contains an eigenvector of, okay? So an eigenvector in U is going to be some linear combination of this C1 CK. So somehow we have to make an eigenvector of this form. Like a C times something, we have to make an eigenvector, okay? This is good. Okay. Now, what else can we say about this matrix R? Because the columns are orthonormal, then which way? Which one? So from the definition of R, R transpose R. R transpose R equals? Okay, there you go. Okay. So now, again, it's useful for problems. You see this, you're looking at the conclusion. What do I want? I want an eigenvector for A. I want A times something on this side. Now on this side I have R, which works in my favor because I want an eigenvector that looks like this, which is exactly R times something. Okay, I already have A and R. I'm looking for some kind of coefficients that will work. Well, then let's look on the right hand side. What do I have? I have R, I have B. What do I like about B? B is square. So because it's square and it's real, it has an eigenvalue and an eigenvector. So let's try to use that and see if it works, okay? So let me erase it. So because B is in here, there is let's say theta in R and let's say V in RK, V not 0, such that B times V equals theta times V. So B is square matrix and it's real. So by the stuff I bored you at the beginning of the lecture, there is a real eigenvalue, real eigenvector, so that happens. And now I have ARB, RBV. So we just take this equation and you multiply both sides by V to the right and see what happens. So from AR equals RB, we get that ARV equals RBV. And now the BV gets replaced by theta V. And this is going to be theta times RV. So now you can be, yeah. So ARV became theta times RV. So the same trick question as before. Can I say that You have to check if it's non-zero. Well, somebody's going to help me. Is it 0 or non-zero? RV, you have it here. You see, like, anytime you multiply the matrix R by a scalar, what do you get? You get a linear combination of the columns. And what were the columns? They were orthonormal, so linearly independent. So you can say because the columns of R are linearly independent, RV is not the zero vector. So I have A times RV equals theta times RV. I have RV is not zero. Do I have to do anything? Well, RV is what? Is a linear combination of the C1, so it's going to be in U. So this implies that RV is an eigenvector of A that is contained in U. Okay, so I think we proved that. Okay. Okay, I lost track. You look through your notes. We had the sequence of steps. This was the one that I just erased. Was step 3. Okay, so obviously. Can I erase on the left side? It's okay? Okay. So, okay, step 4. Okay, let's let K be natural number, K between 1 and n minus 1. What we'll show is that any set U1 UK of orthonormal eigenvectors of A can be extended to a set U1 UK plus 1 of orthonormal So before we go through the proof, let's just see that this step is going to finish the spectral decomposition, because if I'm able to prove this, then I will be able to argue that the space Rn has a basis of orthonormal eigenvectors, because at the beginning we argued that real and symmetric matrix, it will have one eigenvalue, one eigenvector. Okay, so you normalize that eigenvector so that it has length 1. It's an orthonormal system, and then you start with that and you apply this step. So you take that eigenvector, you can extend it to, you can add another eigenvector to it that is, you know, in the complement of it, in the orthogonal complement of it, and you keep doing this until you cannot do it anymore, until you get n, and you're going to have a basis of orthonormal eigenvectors. But this step also, you see, it's general, but it gives you an idea about what to do and where to look for. So you have kind of from the statement, you can get an idea about what you're going to do. So you have U1 UK already some orthonormal eigenvectors, And now what we're saying is that you can add one more eigenvector to it, that this is orthonormal. Like this one having length 1, it's easy. Once you find it, you normalize, that's not a problem. But because of the statement, you know where to look for UK plus 1. If you have U1 UK and you're searching for something that's orthonormal, you want to look for UK plus 1 in the orthogonal complement of the space spanned by this. And that's essentially the idea of the proof. So let's what did I call it? U, W. Okay, let's call it W. Let W be the span of U1 UK. Okay. Now, what's so special about W? Because these are eigenvectors, think about what we've done so far. What can I argue about W? What kind of a subspace it is? Invariant, because U1 UK are eigenvectors. I forget, this is obviously from the definition. W is an A invariant subspace. Okay. A invariant subspace, that's it, of Rn. Okay, so now this is step 4. Which one of the steps 1, 2, 3? It's one that I left you as an exercise. One of the ones I left you as an exercise. If you have an invariant subspace, what else is an invariant? Yeah. Which one was that? 2. By 2, W perp is also and now if you have an invariant, what are you guaranteed to find in there? An eigenvector. This is from step 3. By 3, so you pick an eigenvector there, you make it length 1, and because it's in W perp, it's guaranteed to be perpendicular here, and you're done. Make sense? So yeah, don't be shy about asking questions. I'm sorry if you know all this stuff, but I figure it's good to kind of start. And the thing, again, like the stuff that I showed you about this U invariant subspace, we'll see it again tomorrow when we talk about quotient matrices and equitable partitions and so on. Okay. All right. So I'm not gonna. Okay, you can write the conclusion. So from 4 implies that there is an orthonormal basis of Rn formed by eigenvectors of A. Now, jumping a little bit ahead, because I haven't talked about graphs and adjacency matrices and so on, but I can still give you an exercise. Where are we? Exercise 4? 4? 4. Okay. I assume, consider the adjacency matrix of the complete graph. Kn. Find an orthonormal basis of Rn formed by eigenvectors of A. So just, I'm jumping a little bit ahead, but the complete graph Kn you have all n vertices joined by any 2 vertices, distinct vertices joined by an edge. So here this is K5. And the adjacency matrix of Kn is going to be, you have 0 everywhere and you have 1, or the same thing as all one matrix minus identity. Okay, so just something for you to do. Okay. So now the remaining half an hour, let me give you a different perspective on this thing. So what I show you now, this kind of self-contained proof that every real and symmetric matrix has a real and symmetric matrix has an you can get a basis of eigenvectors that span the whole space, and we will apply this from now on. But I want to show you a different perspective, and it's using which is broader, and it allows you to handle all these spectral decomposition theorems, Hermitian and normal and so on. Now, in this book by Horn and Johnson, if you go in section 2.3, you will find the following quote. Perhaps the most fundamentally useful fact of elementary matrix theory is a theorem attributed to Schur. Okay, then they go on to state. Now, this Schur theorem, I mean, there are many Schur theorems in mathematics, but this one about, let's say, Schur upper triangular theorem. In words, it says the following. Any square complex matrix is unitarily similar to an upper triangular matrix. So if you put no restriction on your matrix and you take any complex matrix, so I will write it down here what I mean by this. So for any a complex matrix, where did I write it? There exists U and T such that, so here it's over complex, so the transpose gets replaced by this conjugate equals T, and so U is unitary, so U star U is identity. You can say, okay, U star U is, so this means U unitary, and T is upper triangular. So T is square, here you have 0. Okay, so you can have here T, you can have here T11, T and N. Below them you can have, I'll put star, you can have whatever you like, but above the main diagonal you have 0. Okay, so this is general. Yeah, question? Huh? Oh, the other way around. Sorry, yeah, I got myself mixed up. You're right. Yeah, you're right. Upper triangular is the other way around. like that. So above the diagonal, you have everything, and below it. Thank you. Very good. So if you have no condition on your matrix, any matrix, the best you can do is it behave like an upper triangular matrix, or of course, lower, the one that I wrote before, lower triangular matrix. Now, this Schur theorem, again, it's a general statement, and let me write it here. So it's going to imply the spectral decomposition theorem for normal matrices spectral decomposition theorem for Hermitian matrices and from which you get the spectral decomposition theorem. Okay, so this one we already saw it, like we saw the self-contained proof. But this spectral, this general theorem, it can give you something for complex matrices. So Hermitian matrices, A complex, such that A equals the complex conjugate, and normal such that A. Now here, if this one gets replaced by A is real, then you replace the star by transpose. Okay, so you've probably done this in linear algebra. I don't know how, what books you used or that, but again, this theorem implies these theorems. Now, what's the statement for each of them? So the statement here is if you have a normal matrix, then A is unitarily similar to a diagonal matrix, and diagonal matrix will have the eigenvalues which are complex for normal. Now for Hermitian, A is unitarily similar to a matrix, and again on the diagonal, on the diagonal you'll see the eigenvalues, and this will be real. There will be real here, and there will be real here. Okay, so here it will be unitarily gets replaced by this real and orthogonal matrix, which is the one by eigenvectors. Okay, so again, I think it's useful for you to know this, to have this broader picture, because when you, again, if you come to encounter papers, like I said, especially now, there's some push about doing something for directed graphs, and there are several papers which study directed graphs, and the approach is having like a 0-1 matrix for these directed graphs. Like it's tricky to find a symmetric matrix, so people look for Hermitian matrices to do something. I know of one paper that is try to do the spectral theory for directed graphs using normal matrices. But normal matrices, because you have this condition, this imposes like it's not may not work for all the directed graphs and so on that you use. Here, this one seemed to be the simplest that you can. And like I said, I may mention a little bit something towards the end of the course, but for now, I wanted for you to be aware of this. Now, okay, so this is you know, this, and this are, they're not hard, but they're not trivial. So you may think that this here, it's some super, like it is a super theorem because it implies all of them, but it's actually not that complicated. So I'll give you a sketch of this and then we finish for the morning, okay? Let me erase here. So I'll just copy the statement from here, from the bottom. So for any A, let's say such that okay. Okay, so the whole thing is here, you give me the A, you're looking for the U, you're looking for the T, okay? Now, in the previous parts, what was U formed by? Like in the case of spectral decomposition for theorem, well, like how can you think of U? The columns are eigenvector. So that's the same idea here. So what you start is, because A is a complex, A has a let's say lambda 1 complex and V, okay, such that so you can take V to be of length 1. Okay. And now what you're looking for? You're looking for U unitary. Okay. So what we do is let's try our first. Let's attempt our first try at U. What we'll do is take U1, a matrix where you put V in the first column, and then you don't know what to fill it up with because you don't know if you will have eigenvectors and so on. But you know for sure that you can do Gram-Schmidt, and you can fill it up with some vectors U2, Un, such that U1 star U1 is identical. So you get you get to start with one vector V1, which you know that every complex matrix is going to have one eigenvalue, one eigenvector. Okay, so you start with that, and then you see, like, you can rewrite this as AU equals U transpose. So the first calculation you'll do is here, A times U. The ones that from, I don't know, experience and so on, you want to pick eigenvectors are going to be your best choice here. And you don't get the full, you may not get the full set of eigenvectors, but you have one. So, okay, you use that. Take one eigenvector. And what are you going to fill it up with? Fill it up with whatever you can. You can fill it up so that this is unitary, okay? And then you say, okay, what is going to be U1 star A U1? So it's U1 star, and now A U1 it's going to be here. It's going to be lambda 1 V, lambda 1 U2, lambda 1 UN. That's when AU1 becomes this. Because when A meets V, it becomes lambda 1V. This one's, yeah, here I'm wrong. Yeah, this is A. Sorry. Yeah, I was got carried away. Okay. Okay. And now, what comes from the left? From the left is U1 star, which is V1 star, U2 star. Okay. And lambda 1, I call it V. So the main thing is we want to see what happens here on the first column. Lambda 1 on the first value. What's the value here? 0. Yeah. So you see, just the simple fact that you took this as an orthonormal basis, it clears out your first column. Okay? And then you're going to get something here, and you're going to get something here. I don't know, let's call it A2. Okay, so now now you kind of see the idea. What's the idea? You want to get to upper triangular. You already cleared up the first column. You want to go inside here, and you want to clear up the same thing. So you do the same thing. A2 is a complex matrix. You pick an eigenvector, fill it up with a unitary. Now you still have to do this calculation for the big matrix. A2 is n minus 1 by n minus 1. So you just put a 1 in front. You kind of border them with a 1 on top. And you do the same calculation, and you see that this procedure will allow you to clear up the whole thing here. Okay, so it's essentially, what is it? It's Gram-Schmidt. Like you and the fact that you have one eigenvector to start with. Like you need that eigenvector to get you here, to get you this value on this position. Okay, and now this is how you get an upper triangular. Now this theorem, as you see, because your matrix is complex, you get upper triangular. But then when you put these conditions on your matrix to be normal, Hermitian, and so on, that's going to force this upper triangular to be the same as them, to be normal, Hermitian, real, and symmetric. And that's going to force the upper triangular matrix to be a diagonal matrix, and that's gonna do it. Make sense? Yeah. Questions? No? Okay. Yeah. Can you speak louder? I can't hear. Then you don't need anything else. You are like, that's kind of the place. That is, in some sense, that's the happiest situation that you can be, because that's the same thing as having like this orthonormal basis. Yeah. Yeah. You can do this calculation. Yeah. Like if you so you're saying if A is unitarily similar to a diagonal matrix, then okay, exercise what number? 5. Exercise 5. There you go. You answer your questions already. So don't be scared. Just because you ask a question doesn't mean you get an extra exercise, but sometimes it can happen. So okay. Okay. Now, one more quick thing. So in the book by Horn and Johnson, they don't have this diagram, but they have a bunch of consequences of this. And like I said, it's a really, really useful theorem, and it has many consequences, not just this. It has a consequence that you may, sometimes when you're a student, you may struggle to remember Cayley-Hamilton theorem. You can remember Cayley-Hamilton theorem. You have characteristic polynomial, you plug in the adjacency matrix, you're going to get the zero matrix. And it's easy to remember the wrong proof of Cayley-Hamilton theorem. Which one is that? You take characteristic polynomial and you replace the x by a. And so therefore determinant is 0, so you're done. So that's the wrong proof. But the sure upper triangular theorem, what it does, it allows you when you're dealing with your matrix, you can replace it by upper triangular. And for upper triangular theorem, this Cayley-Hamilton theorem is it works. It is still some work. I'm not going to do it here, and we're not going to do it in the exercises. But it's another. And there are many other consequences that that are in the book, but I'm not going to do here. But for us, these are like the important ones, and especially this one that we've already done. Okay, so I thought I'd mention it. I got this. Okay, I'm supposed to talk about Perron-Frobenius. Now, let's talk about that quickly. I have 10, 15 minutes, so let's talk about Perron-Frobenius. Can I erase here? Okay. So now we can go into talk about graphs and all that. So here's a notation that I'll use for graphs. So graphs and matrices. So I'll have gamma VE. That's the notation that I will use for. So again, this will be undirected graph. And now to a graph, you can associate infinitely many matrices. You can define all kinds of matrices. The most popular ones are going to be the adjacency matrix. So this will be A of gamma. And let's do it by an example. So let's say this is my graph, vertices 1, 2, 3, 4. Okay, just a silly graph. And the adjacency matrix, so the rows and columns of A are labeled by V, by the vertex set. And then in the position XY, we write down the number of edges between X and Y. And this is kind of the general for multigraphs or loops and so on. Since I'm not going to talk about that, at least for the first few days. So if the graph is simple, so a graph is simple if you don't have multiple edges or loops or anything like that, then here you can just say AXY is going to be 1 if X is adjacent to Y and 0 otherwise. So from this graph, the adjacency matrix 1, 2, 3, 4, 1, 2, 3, 4, 0, 0, 0, 0, and then I have edge everywhere except 1, 1, 1, 1, 1, 1, 0, 0, 1. Okay, yeah. Now the second matrix that people study, so this is the adjacency matrix. So the Laplacian matrix it's usually denoted by L or L of gamma. And for now, I'll just give you the entry-wise definition. So again, the rows and columns are labeled by V. And if you have L of xy, now you're going to have three things. It's going to be the degree of x if x equals y. So I'll tell you in a second what the degree is. It's going to be -1 if x is adjacent to y, and it's going to be 0 otherwise. So the degree of x this is the number of edges, the number of neighbors of x. So here, if you want to do L, the same thing, 1, 2, 3, 4. So this one has degree 3, 1 because it has 3, and then 2 has degree 2, 3 has degree 3, and this one has degree 2, and then you have -1, -1, -1, -0, 0. So these are the main matrices that we'll study in this class: adjacency matrix and Laplacian. There are many other matrices, like I said. There's signless Laplacian, normalized Laplacian. Distance matrix will come up in some play a little bit later, but this will be the main matrices we'll study. Okay, so I think I'll leave Perron-Frobenius for well. Maybe I'll state it, and then we can discuss it after the break. Okay. So again, because we're looking at undirected, that's all these matrices that we'll have will be real and symmetric, and you get this kind of useful fact that you have a basis of orthonormals immediately, and that's going to drive most of the things that we'll do with eigenvalues and eigenvectors. Now, here's one thing we're going to do after the break. So this will be, so there is something called Perron-Frobenius theorem. So I'll give you the light version for undirected graphs, light version. This implies that there is a more general version. There is a general version for something called irreducible matrices, but we'll do this for undirected graphs. And he says the following: let gamma be a connected graph. Now, we'll talk about the eigenvalues of the adjacency matrix. So denote. This will be the notation we'll use by λ1 greater or equal to λ2 greater or equal to λn, the eigenvalues of A. So here you see I put greater or equal, so you could have repeats, but in total I have n eigenvalues because I have n orthonormal eigenvectors. So that's my notation. λ1 is the largest. Then 1. So this is a connected graph. So again, we assume we have at least one edge and so on. So then λ1 is positive actually. λ1 is going to be strictly greater than the absolute value of λj for any j from 2 to n. So this λ1 it's a positive and it's the largest. It's largest, but it's also, you could say, well, here maybe I get something negative, and that something negative is very negative. Well, it cannot be very negative because it's what is it? What's it called? Yeah, that's a very good yeah, that's a very good. So maybe yeah, you have a very good point. So let me put it this way: λ1 bigger than, greater or equal than absolute value of λn. You're very good, yeah. And 2. Yeah, I got it. Lambda 1 bigger than lambda 2. That's what I wanted to say. Lambda 1 is bigger than lambda 2. And then 3, you can find the multiplicity of lambda 1 is 1, and its eigenspace is spanned by an eigenvector with positive entries. Okay, yeah. So in absolute value, it's greater or equal to 10. So lambda 1 is positive, is greater or equal than absolute value lambda n. Thank you about the bipartite. Lambda 1, here you have actually strict inequality. It's always going to be the winner, only one winner. And then the dimension, yeah, because of that, lambda 1 is strictly bigger than lambda 2. The multiplicity is 1. So that's the same thing as lambda 1 bigger than lambda 2. And the eigenspace, you can find an eigenvector whose entries are all positive. Obviously, you can multiply by -1, you get all the entries negative as well, but positive, it's better to be positive than negative. Okay, so yeah. So I'll stop here and then we do this after the break. Thank you. Okay. Think about it. Yeah, but it's still. So think here your here is increment. Yeah, the one that yeah. Okay, so we can discuss it, but we're saying that if you have all these three conditions, then the graph has to be. Yes, I think the hardest thing is if you look at yeah, right. You have to the one that I initially said if you just take one of them, you have to just the but so write it down like 1, 2, and 3, 1 and 3. So let's think about it. Yeah. Yeah. Yes. Uh, yeah. Yes. Yes. Uh, yeah. You can. I mean, if you. Yes, you're right. So you can say it has to be. I mean, at the end, because A is symmetric, then yeah, I understand, but basically the argument here is that if B will have that eigenvalue, but the argument yeah, I think I can get here, but I think at the end you can still argue that you're right. His point is that at this initial step, you cannot say that B is symmetric. B is a square matrix is it's a good point. And his point is that I cannot just say B is I mean, at the end, it's going to be values just a matter of because again, the eigenvalue of B becomes an eigenvalue of A. But you're right, I take correct because of the first step, say B value. You don't. So that's right. Yeah, you're right. Thank you. I don't think you can argue that B is from that. Usually, if R is square, you can move things around it. So, but R is not square. Yeah. So, I think this is the element of B has It's very good. Yes. Yeah. Exactly. Yeah. I think just those yeah, I think my impression is that yeah, 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 yeah. Okay. Say, Next one. You know, this particular thing.
లేవలేదు అంకుల్ ఫోన్ లేపుతలేడు ఎవరు వచ్చారు ఓకే నేను షూట్లో వాడు లేపిండి వాళ్ళు లేవలే అవును ఓకే ఓకే ఆడు వచ్చాక ఒకసారి కాల్ చేయమన్నా 7:30 ఏడను ఏడిపోతాను ఎందుకు హీరో ఇప్పుడు మనకి ఏమైంది వాడు పోతాడు కదా నువ్వెందుకు పోయినావు మరి బరకలేవా నీకు వేసిర్రు వీడియో తీయాలి యూట్యూబ్లో చూడు అట్లాంటి వీడియోస్ ఉన్నాయి అట్లా వేసేసి సరే చూసి పెడతా పోయినాక అయితే చేయి
Hello, sir. Friday or today? Friday. Okay.
Okay.
Take this water.
Huh?
Are you okay with this? This
What?
water.
Oh, yeah. This is mine?
I think all three are yours.
Okay. Yeah. Uh, okay, let me move this that way. So this one goes one,
One.
1 and 5. Yeah.
Maybe 10 minutes earlier also you can stop.
Okay. That's good. Yeah.
Ideally 1 hour 15 minutes to 1.5 hours.
Hmm?
1 hour 15 minutes to 1.5 hour you can keep.
Yeah. So I can start?
Yeah.
Yeah. Okay. Okay. Welcome back. So before we start, just a few questions some of you asked. I'll leave this here. Let me erase here. So one of you asked the following question about the proof that we did about the self-contained proof of a real and symmetric matrix has a basis of, you get a basis of orthonormal eigenvectors. So in that proof we had something of this form: AR equals RB. What was happening is that R was this tall matrix, K, and then K, and the columns of R were like the, an orthonormal basis. So therefore, you have what? R transpose R equals IK. Okay. So the argument here was, so what we had is R transpose AR equals B, and then we say, okay, B. Well, we left it like this. So from here, what did I say? B was a small k by k matrix. And I argued that, okay, B has an, eigenvalue theta and eigenvector, I forget what we call it, V. Okay. So the question that one of your colleagues asked is, okay, how do you know this theta is real, this V is real? Okay. So I guess I didn't mention it in the proof, but you can go back, and so you have AR equals RB. You multiply to the left by R transpose, so you get R transpose AR equals B. And what is this going to tell you about B? is symmetric. So because B is symmetric and it's real, then you're gonna get here that has to be real eigenvalues and eigenvectors. So I just, yeah, that's a very good point. I'm sorry for not mentioning earlier, but that's, yeah, B is a symmetric matrix, so that guarantees real eigenvalue, real eigenvector.
Is the matrix A symmetric?
Yeah. Because yes, because this is the stuff that we're doing. We're doing it for real and symmetric matrices. Yeah. So this is this. I think it was last step 4, where we wanted to show that. It was step 3 where we wanted to show that if you have any A invariant subspace, it contains an eigenvector of the matrix, and we took the A invariant subspace. We take the columns to be a basis, orthonormal basis for that subspace. So because of that because of A invariant, A times R is going to be a linear combination of R's so you get this. And again, yes, that's a very good point. You need A to be symmetric to guarantee that B is symmetric. So you see, it's useful to go through these proofs to kind of see the key junctions where the assumption about your matrix is used. The fact that symmetric is helpful. Like you saw from the other part, like the approach using short upper triangular theorem, you see there that symmetric plays a role there, because if you're looking at upper triangular matrices that are symmetric, you're forced to be diagonal. Here, this is the place where symmetric is used, that B is guaranteed to be symmetric, real, and so on, and that's your done. Okay, so I just wanted to clarify this before we go. Okay. So again, if you have questions, and if I miss steps or if I skip anything, just write it down. I already got some question about this already. I didn't even go through the proof, but people were asking about converse and so on, so we can talk about that, so on. And if you have questions and comments, you can write them down, and in the afternoon, I'll be more than happy to ask you to come to the blackboard and try to see how it is to lecture 50 students and so on. So we can do that. Okay. All right. So yeah, thank you about catching this thing about lambda 1 greater or equal to lambda n. Okay, so here, gamma connected graph, let's just put something on n greater or equal to 2 vertices. So that, because if I have one vertex, there's the 0 matrix, so lambda 1 will be 0, so we'll just avoid that, okay? Okay. So again, the part that we did earlier, the fact that we have real and symmetric guarantees that we can order the eigenvalues, the real lambda 1 to lambda n. Now, what tells you that lambda 1 is positive? The simplest proof, lambda 1 is positive. Yes, trace. So, so trace of A, because it's undirected, so it's because gamma is simple. 0 is the trace of A, which is lambda 1 plus lambda n. Okay. So what does it imply?
It has some positive and negative eigenvalues.
What?
It has some positive and negative eigenvalues.
Why can it have all
At least one.
Yes, they're real. And? Okay, so that's what I'm asking. We're kind of going around the circle and it's all, so why at least one is positive? Oh, you can say, well, because at least one is negative. Okay, and then why is that? You cannot go again because one is positive, because there cannot be all. Really? Yeah, all cannot be, yeah. All cannot be positive, all cannot be negative, but all cannot be 0. Why all cannot be 0? because the graph will be 0, 1. Okay, so because gamma is connected, so not all eigenvalues can be 0, and so you'll have some positive and you'll have, well, you'll have something non-zero. And why can't you have lambda 1 be 0 and everything else negative?
Sum should be 0, so that implies everything.
Sum is 0. Yes, there you go. Okay, so from here, figure out the details. Lambda 1 is going to be positive. Okay. You will see it will come up from something like this about the eigenspace is spanned by an eigenvector. So let's try first. I want to convince you that you can find there is an so claim there is an eigenvector corresponding to lambda 1 that has okay. So there are several ways to do this. Again, after we go through some of these ideas of this proof, we're gonna state the one for general matrices like irreducible matrices, where these things will be true plus some extra stuff. Now, for this proof, what do we have? We have a u1 equals lambda 1 u1 for some u1, which is real, which is not 0. And so what guarantees that we have an eigenvector? The first theorem that we did in class, that it's real symmetric, you have an, but spectral decomposition, you're going to have an eigenvector here. How do we go about, because I mean, if you just say any eigenvector will have these properties, it's not going to be true. It's not true that every eigenvector here has positive entries. So if somebody wakes you up at night and says, okay, here's my matrix, here's my eigenvalue, where do we go to find an eigenvector that's going to be positive? Okay, so I'll give you a couple of proofs of this statement. So let's see. Now, here you see this will come up because we'll talk about Rayleigh quotients and so on. Whenever you have a u1 equals lambda u1, you multiply to the left by u1 transpose, and you're going to get something like this. Okay, you multiply to the left. And now maybe we want to make our life easier. So let's take, if I have an eigenvector, I can always divide it by its norm, and I can normalize, I can make it of length 1. And that way, so I can say here u1 transpose u1, which is the length of u1 is 1. And in that case, you get your lambda 1 just here. Okay? All right. So lambda 1 is going to be u1 transpose a u1, and you can expand this, and this is going to be a summation x, y in V of a x, y u1 x times u1y. So this is an example of this Rayleigh quotient of a matrix associated to some vector. Okay. And now, so what I want is I just picked one eigenvector, and I want to make some kind of eigenvector that has all the entries positive. Okay. So I might as well, let's just define v1. v1 of x is going to be the absolute value of u1 of x. Okay. So what I'm doing is, okay, if this u1 had let's say positive, negative eigenvalues and so on, I just bring them everything on one side. Obviously, you have to worry about, okay, what happens if I had 0? That's where we have to deal with. Okay. Now, before we do this, here's the first. Okay, I'll leave this here. Claim I'll. Here's the first this place where this Rayleigh quotient will make an appearance. So this Rayleigh quotient is going to be Rayleigh quotient of a vector with correspond with an eigen and a matrix. So, and it's going to be something, let me call it RAU. I will just use this notation at the beginning now. Maybe I have U there, so let me use W. This is going to be W transpose A W, W transpose W. And this is defined for a matrix A and this vector, which is not 0 vector. Okay. Okay. And now in course of our, one thing that we will use is that lambda1, the largest eigenvalue, is going to be the maximum over all W non-zero of this Rayleigh quotient, W transpose A W divided by W transpose W. And if you normalize W, you can just take W of norm 1. So it's maximum overall, I don't know, let me call it V, such that the length of V is 1 of V transpose A. Okay. So this is a claim that you take this this expression, this one or this one, and you maximize over all possible vectors. Here, all non-zero vectors. Here, all vectors of length 1. The maximum will always be, yeah, okay. So this is a bit the simplest case of this type of max-min inequalities about Rayleigh quotients and eigenvalues. And let's go to, do you guys all know this, or should I go through it? Go through it? Okay, okay. Let's go through the proof. Okay. Okay, so there are two things. The fact that here it's max, you have to be careful sometimes. In order, if it's maximum, it means it has to be attained. So okay, because otherwise you put supremum if it's not attained. So in order to prove this, we're going to show two things. So we're going to show thing one. We'll show that for any W in Rn, W less than or equal to 0, lambda 1 is greater or equal than okay, so lambda 1 wins all the time. And second, that there exists some vector W in Rn, W is not 0, such that lambda 1 equals okay. Sorry, I kind of got stuck in the middle of this proof, and I realized I need this claim. So I'll just do it here. Okay. Okay, I'll erase here and I'll come back to this in a second. Okay, so proof of one, proof inside a proof. And here, this is the place where you use this spectral decomposition. So if you take W in Rn, now I didn't mention, but my matrix A is going to have eigenvalues lambda 1, lambda 2, lambda n, and I can take a basis. So I'll fix myself a basis. I'll pick an eigenvalue for each of them such that this is orthonormal basis for Rn. And these are eigenvectors. All of them are eigenvectors. U1 corresponding to lambda 1, U2 to lambda 2. Okay? So if you have W here, then W is going to be alpha 1 U1 plus alpha n UN for some reals, and because W is non-zero, not all of them cannot be zero. Not all zero. Okay? And then the reason these expressions come into play here is that they play well with orthonormal basis. Everything works out very nicely. So for example, okay, we're gonna do the two computation. W transpose W, this is so alpha 1 plus alpha n transpose times alpha 1 plus alpha n un. And when these vectors from here meet these vectors from here, only the ones that have the same index survive, and you'll have alpha 1 length of u1 square plus alpha, so alpha 1 square, alpha n square. But all these lengths, that's why you take unitary, because it makes your life easier here. So it's going to be alpha 1 square plus alpha n square. Okay? And this is going to be positive because not all of them are zero. Okay. And then the other calculation is W transpose AW. But let me do first AW is going to be A times alpha 1 U1 plus alpha n UN. And then it's alpha 1 A1 AU1 plus alpha n AUN. So alpha 1 lambda 1 U1 plus alpha n lambda n UN. So A just contracts or deletes the vector by a little bit, and then it behaves nicely when we multiply this to the left by W transpose. So you're going to have alpha 1 U1 transpose plus alpha n UN transpose lambda 1 alpha 1 U1 plus lambda n alpha n UN. And it's almost the same. It's almost the same as here, but you have the lambda ones in there. The same thing happens orthonormal. They kind of cancel each other. So you're gonna have what? Lambda 1 alpha 1 square plus lambda n alpha n square. Okay, so all this work to give us what? To give us that W transpose AW divided by W transpose equals, on the top we have this, and now, I mean, if you look at this expression, this is a convex combination of the lambda 1 lambda n, because you can write in many ways. Let me alpha 1 squared divided by the sum of all the alpha j square lambda 1 plus alpha 2 square divided by the sum of all j equals 1 of alpha j square lambda 2 plus alpha n square divided by the sum from j equals 1 to n of alpha j square lambda n. Okay. And the thing that I wanted to show is that lambda 1 wins, so you don't need this expression. I just wrote it so that you can remember it, but you can go here and you look here, lambda 1, lambda 2, lambda n, which one is the lambda 1? So then you're going to have less than or equal than lambda 1. So okay. So it's useful to do this calculation. Sometimes this is quite common, and like I said, we'll see it in the max-min theorems and so on. Sometimes the W may not. Sometimes you may know that W comes from a smaller subspace, and it's generated maybe by the first k eigenvectors from here, or from the last k eigenvectors from there. So you can play the same game, and you can always know. You will always know where the maximum and the minimum lies of this expression. It's like the largest of your eigenvalues, the smallest, and so on. Okay, so it's the same trick. Okay, so this proves 1. And for 2, it's very easy. You just take, so for the proof of 2, you take W to be U1, the eigenvector of lambda 1. So then A U1 equals lambda 1 U1 implies that what we wanted, that W1 transpose A W1 equals lambda 1 U1 transpose U1. So that's, and because U1 is not 0, you can divide. Okay. All right. So that's okay. That's the claim. Okay. I'll erase the proof. Okay. So let's come back to the Perron-Frobenius stuff. So I have a U1. So I have A U1 equals lambda 1 U1. Let me put this. Okay. And like I said, I can take. Let me take U1 to be of length 1. So then I do the same calculation as before, and I have that lambda 1 is U1 transpose A U1. So it's the sum over xy in V, AXY U1x U1y. Okay. So now I want to make a positive eigenvector. So I'm going to define V1 in Rn with V1 of x to be the absolute value of U1 of x. So far I don't know. I could have 0, so I can say greater or equal to 0. And again, because U1 has length 1, U1 is not 0, it's guaranteed that V1 is going to have at least one positive entry. Okay, cannot be all 0. Okay. Now the first thing you do is you calculate this V1 transpose A V1. And it's the same expression there, but now by the second part here, this is a maximum. I'm sorry for using the same letters V's. And I have V1, this is V. So this is a maximum over all vectors of length 1. I didn't do the calculation here, but you know how to do it. This is, what's the relation between this V1 transpose A V1 and lambda 1? Which one wins? Which one is bigger? Lambda 1. So lambda 1 is greater or equal than that. This is this. which is summation over all xy in V of a xy, absolute value of u1x, absolute value of u1y. How is this compared to this? I will forgive me for using this. This is greater or equal than this. Okay, so lambda 1 greater or equal than this is this, greater or equal than this comes back to lambda 1. Huh? So they must be equal, very good. What else? Then V1 is can we say, because so V1 so V1 is guaranteed to be greater or equal to 0. So when I write, okay, is guaranteed, all the entries are greater or equal to 0. There's at least one that is positive, guaranteed. But yeah, so you have to place. Some of them could be 0. But before we get to that, lambda 1, because of all these equalities, what can you say about V1 and lambda 1? Eigenvector. V1 is an eigenvector. For lambda 1. Okay, so now let's say this is my graph. Okay, you have the graph, it's connected. And now we kind of picked this one because we thought that this is going to be the one that's going to be positive. So you have to play kind of devil's advocate, which is figure out what happens. Okay, let's say here, let's put our money on something. Let's make a claim. For every x in V, V1x is positive. Okay, so let's see. Now, like I said before, because U1 is non-zero vector, V1 is guaranteed to have some positive entries, but it may have some 0. So what you can have plus, 0, 0, I don't know, plus 0, plus, I don't know. It may not even be right. Okay, but pretty much you're guaranteed. So let me do another picture here. You're guaranteed that you can split it. If that's the case, you can have all the pluses on one side and you'll have the zeros on one side. Because the graph is connected. I mean, this doesn't use the fact that it's connected. I'm going to use it now. But so what I want to show that everywhere it's plus, 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 plus. There's no 0. You can assume there are some zeros. Because the graph is connected, what's guaranteed between the plus and the zeros? There are several characterizations of connected graphs. A graph is connected, what's the definition? Between any two vertices, there is a path between them, but there is another one in terms of partitions. For any partition, yes, there is at least one edge from the positive side to this side. So there's going to be an edge like this. Okay? So let's see what happens in that case. So let me just write down what we talked about. So the entries of V1 are non-negative, and there is at least one positive entry in V1. Okay? Now, by contradiction, assume that V1 has some 0 entries. Okay? And now we say because now the connectivity, because so far we haven't used connectivity anywhere. Like there hasn't been anything about connectivity. It was just about symmetric matrix. Because gamma is connected, there is an edge. Let me call it AB of gamma, such that V1 hat of A is positive and V1 of B is 0. Like this would be the edge, like there is an edge from the positive side over there. Okay. So now it's a proof by contradiction, so we need to find something wrong. We need to find a problem. So for this one, you go, V1 is an eigenvector. So because it's an eigenvector, you have AV1 equals lambda 1 V1. And then you specialize it on, look at this at the B entry. So you got, let me write it this way, lambda 1 V1 in the position B, let's say B, equals the AV1 in the position B. Lambda 1 V1 in B, so this means lambda 1 V1 B, which is 0, is going to be what? It's going to be AV1 in B. AV1 in B, it's a sum over what? Over all, let's say, C adjacent to B, I'll write it like this, of V1C. So I'm writing this a bit faster. Maybe let me do it in one, before I do this, let me do it like this. So AV1, it's the matrix A multiplied by V1, so it's the sum, let's say, over all Z in V of A, what is it? A, B, Z, V1, Z. You take the row, the B row of A, and you multiply it with the vector V1. But A is a 0, 1 matrix. So the only ones that survive in this sum, the only Z's that survive, are going to be the Z's where A, B, Z is 1, and those are the ones that are adjacent to B. So your B, you're going to be here, you have A, but they could be more. So this is going to be summation over all Z adjacent to B of V1Z. Okay. So what do you know about these entries? All of them are greater or equal to 0, and there is one that is positive. So this is greater or equal than V1A, which is positive. And so that's a contradiction. And that's okay. Yes, yes.
So to prove V1 transpose A V1 equals lambda implies V1 is an eigenvector of lambda 1. We need an argument. Is that mean?
Well, here we see like so U1, I erased it here. U1 is of length 1. That means that V1 will have length 1. And then here, what did we prove? All this argument, lambda 1 greater or equal to this. This is because lambda 1 is the maximum. Equals this, greater or equal to this, ended up at lambda 1. So you have to have equalities everywhere. Very good point. And now, he's asking a very good question. So where are we with exercises? Oh, you can thank your colleague for more exercises. X6 one. Okay. So exercise 6. Exactly here you have V1 in Rn. Norm of V1 is 1. And you have that lambda 1 equals V1 transpose A V1. This implies V1 is an eigenvector. The proof is the same. Again, the spectral decomposition, you always, because you take this V1, you write it down as a linear combination of, now you have to have a different notation because you need to separate your eigenvalues into distinct eigenvalues. Lambda 1 is the largest, then you write down the distinct ones. And this V1 is going to have a component for each of these kind of eigenvectors. But because of this equation here, from the spectral decomposition, you will get that V1 is just a linear combination of the vectors that correspond to lambda 1. So V1, but you have to write it. I'm not going to write it, but so exercise 6, okay? Yeah, so that's a key here because you want, yeah, that's what I used here. Yeah. So that exercise has a little bit of a converse. It's, you have, when you plug in the eigenvector into the Rayleigh quotient, you get the eigenvalue for the largest eigenvalue. If a Rayleigh quotient gives you the largest eigenvalue, that eigenvector has to be that vector has to be an eigenvector. That's all. Okay. 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 So we did this. Let me see if I give you a different proof. Okay. Let me give you a slightly different proof of this result. I'll just give you the sketch. So this one is kind of dealing directly with these eigenvectors and zeros and positive and so on. Let me give you a slightly different proof. I'll just erase here. So. So maybe second proof, positivity of U1. Okay. So now the same thing as before. You see, like this argument, you take an eigenvector, you take the absolute value, you get something greater or equal to 0. But now, so let's say I have again a V1 equals lambda 1 V1, V1 greater or equal to 0. Let's assume length of this is 1. So over there, we just gave an argument that V1 has to be positive by doing this eigenvector equation. You can do it in a different way. You can prove that V1 is positive. And this is kind of related to the matrices that are used a little bit in the proof of the Perron-Frobenius in general. So you can take as a matrix the following matrix. You can take something like I plus A squared plus A and minus 1. I'll tell you in a second why you can take this matrix, or you can take you have more choices than a matrix here. Now, what's so special about this matrix? Because again, gamma is connected, and there's something that I haven't proved yet, that the entries of the powers of A count the number of walks between vertices in the graph. So gamma is connected, you're guaranteed that A is a 0-1 matrix, but when you take all these powers all the way to n minus 1 and you add them up, what are you guaranteed about M? Everything is positive. So all the entries of M are positive. Okay, now this is not the only choice, and again, here's okay, exercise 7. Gamma connected if and only if this matrix I plus A has positive entries. Yeah. You can take this, or you can take, if you don't like this matrix, you can also take I plus A to the n minus 1. Essentially, any linear combination of I, A square, A minus 1 with positive coefficients is gonna do it, okay? Because of this business of counting the walks. Okay, so one thing is M are positive, but there's something else, because you wanna get to V1. So A V1 is lambda 1 V1. So V1 is also an eigenvector for M. Yeah. So from here, you're gonna get M V1 is gonna be something, okay, 1 plus lambda 1 plus lambda 1 n minus 1 times V1. Okay. So now you can give, from here, you can give another proof that all the entries of V1 are positive, again by contradiction. V1 is greater or equal to 0. So assume that you have an entry that is going to be 0. You look at, so essentially you pick up that entry from your vector V1, and you look at this equation at that entry. And so on one side you're going to get 0. On the other side, what are you going to get? Well, if this entry is 0, my vector V1 cannot be the 0 vector. So there's something outside of it that is non-zero, and it's going to meet an entry from M, which is also positive, and is gonna burst into flames and go. So that's the proof. That's a different proof of this. Okay. Okay. All right. Let me erase here. Okay. Okay, so what did we do? We did this. We did that. We have a positive eigenvector. We didn't do the multiplicity. Yeah. Here again? Okay. So here, this entry, this M is all positive entries. Okay. This is also positive. Okay. So now what do you want to show? You want to show V1 is already greater or equal to 0. So you want to show that, so from here, let me put it here, claim, again, for any x in V, V1x is positive. Okay? So the proof is again by contradiction. So assume there is, I don't know, some vertex, I'm going to give it a different name, A, no, I use A, B, C, I'll use D, I don't know, Y, in V, such that V1Y is 0. Okay? Now here I have M V1 times something positive, let's call it f of lambda 1 times V1. So now we look at the entry Y in both of these places. So you look at what is f lambda 1 V1 in the position Y is equals M V1 in the position Y. Now here, you know what you're going to find. You're going to find f lambda 1 times V1Y, which is 0. Now, what am I going to find here? Now, here, M is not a adjacency matrix. It has like, all the entries are positive, so they're going to be bigger than 1, but you write it down. It's a summation of what? Over all Z, Z in V, M, Y, Z, V1, Z. Okay? Now, every one of these entries is positive. But now V1 is not a zero vector. And V1 is also greater or equal to 0. So there's going to be one of these Z's, not all, at the end, all of them are positive, but at this point, you only know that one of them is positive, at least one of them. So at least one Z has V1 of Z positive. So you see the game is fairly simple. You move from A because A works in your favor, but you have 0 entries, and the 0 entries mess up your thing. So then you move from A. How can I make from A a matrix which has all positive entries? And like I said, this is one way, or this is another way, or you can take, there are many ways. But you take an M, which has positive entries, that's going to have the same eigenvectors as A. And then you get to here. Does it make sense? Is it clear? Yeah, perfect. Thank you. Okay. Okay, second proof. Let me erase here. Okay. So we can add it to exercise 7. I don't want to make exercise 8. Just put it here. If and only if I plus A has positive entries. And now think about if this n minus 1 can be reduced to another number. Okay. That depends on the graph. Okay. So. Okay. Okay, so let's do this one first, and then we can do this one. So let's prove. Or let me see, which one do I want to do next? Okay. Yeah, let's do this one because it's easier. This one. So let me prove that absolute value of lambda n is less than or equal than lambda 1. Claim. Okay. Again, it helps to think of lambda 1 as an eigenvalue, but to think about it as this kind of optimum of this Rayleigh quotient business. Because if you think about that, then things kind of orient in the right way, and you have lambda 1 greater or equal than something. So earlier, we saw here that lambda 1 was the maximum of all Rayleigh quotients and all that stuff. So lambda 1 beats all the Rayleigh quotient. So maybe it will beat something that involves this. So that's kind of the idea. So proof. So you take un in Rn, un not 0. Well, un, let's say, of length 1 as before, such that lambda n a times un equals lambda n times un. And as before, therefore, un transpose a un equals lambda n. So you got your hands on lambda n from here. Okay. Now, what do you want here? You want absolute value. So take absolute value. So you have absolute value of lambda n is absolute value of un transpose a un. And this is going to be absolute value summation over all xy in V, AXY UNX UNY, and then use triangle inequality is going to be less than or equal than the summation over all xy in V of AXY UNX UNY. Yeah. Now, if the vector UN has length 1, if I replace all the entries in the vector UN by their absolute values, that vector also going to have length 1. So from here, if I take the absolute value of this vector UN, the length of it is also going to be 1. Okay? If you square the number or square the absolute value, it's the same thing. So here, what do you have here? Here, this is a Rayleigh quotient. This is the same thing as this vector UN. Let me write it like this. A transpose. So I'm sorry for the notation. I'm introducing notation here. This notation is the vector where all the entries are the absolute values of the UN. But what do you know about the Rayleigh quotient of any vector of length 1? Who is the boss of all of them? Who beats all of them? Lambda 1. So that's it. So that's that. Okay. Okay, so let's do now the multiplicity business. Where do I have it here? Okay, so we're gonna follow the same script. So claim not strictly lambda 1. Okay, so we'll follow the same script from here. So because again, you see like the way you can guide sometimes, you see which side is lambda 1. Lambda 1 is a side that is greater or equal. So it kind of, okay, maybe I use this thing about lambda 1 being the maximum of all these Rayleigh quotients. So again, consider, let's say U2 in Rn, norm of U2 is 1, such that A U2 equals lambda to U2. Okay, and we do the same type of argument. Therefore, lambda 2 is going to be U2 transpose A U2. And let me see if I need absolute value. Yeah, so I'll take again V2. So define V2 in Rn by V2 of x equals the absolute value of U2x for x in Rn. And then, okay, so we'll do this. Lambda 2 is this. Now this is going to be the sum over all xy in V, AXY, U2x, U2y. And now we're going to say less than or equal than the summation over all xy in V of AXY, absolute value of U2x, absolute value of U2y, which is the Rayleigh quotient of V2 transpose A V2, and that's going to be less than or equal than lambda 1. Okay. So it almost works. So you have lambda 2 this from here. Then this is algebra. Less than or equal because absolute value beats the number. And this is of another vector, which is less than or equal to lambda 1. But the thing is, what do we want somewhere here? You want some strict inequality. So let's see, how do we find a strict inequality? Well, there's another thing that we haven't. Okay. What can we assume about Okay. These vectors u1, u2, un are what? Orthonormal. So one thing we haven't used about u1 and u2. They're perpendicular on each other. So you know for sure, we know that u1 is positive. We can take u1 to be a positive eigenvector. And u2 is going to be perpendicular to it. So u2 is guaranteed to have what? Negative and positive, and you could have zeros, okay? So here, let me, the proof goes by two cases. So case one, let's say u2x is not zero for any x in V. So if u2x is not zero for any x in V, it means that if you take your graph and you split it according to the entries in u2, you're going to have again pluses and minuses, because this fact is because u2 is perpendicular on u1. u1 is positive, so it's going to be a linear combination of the entries in u2 is going to be 0. u2 is not 0, so you'll have positive or negative, and once you have positive, you're going to be forced to have negative by this condition. And because this assumption that, let's say, none of the entries are 0, it's going to be split in positive and negative. Then where can I find some strict inequality here? You can find a strict inequality here because, again, what are you going to use? The graph being connected, it means that there's going to be some kind of edge here that goes from positive to negative. There is some edge AB where the entry here is positive, the entry here is negative. So if you look here, U2A times U2B, so A is positive, B is negative, so this is going to be negative, and then this is going to be strictly less than absolute value of U2A, U2B. Make sense? Huh? Well, so this is a case where there are no zeros. So the case where there are no zeros, you separate into positive and negative, and we kind of did this before. And again, you see the place where gamma being connected plays a part. There is a place where you have something positive, something negative, and then this will guarantee you here that it's going to be, you will have a strict inequality, okay? So that's this part. Okay, so obviously case one is the easier one, but you know, not everything in life is easy like case one. So you have also case two. U2 So there is a possibility that this u2 of x may be 0. Okay, why is this won't happen? It cannot happen at the same time as with equality throughout. That's what you're saying. Because again, the game is we want to show that there's strict inequality here or here. If you have inequalities, so first, if you have equality here, what does it tell you about V2? It's an eigenvector of, yeah, and then there is something there. So where are we with exercises? Okay, exercise 8, finish here. Finish the proof here, okay? Okay. Oh, okay. Okay, so now let's do something about spectral graph theory. So let's do a theorem. So let gamma be a graph with adjacency matrix X. 1. So this will be one of the first results where you will see this connection between combinatorial properties on one side and eigenvalue properties on the other side. And it's probably familiar to most of you, but let's do it. If gamma is bipartite, then the spectrum, which I haven't said what it is, but I'll mention in a second. So the collection of all the eigenvalues of A is symmetric with respect to 0. So what do I mean by this? I mean, if let me say, if lambda is an eigenvalue of A with multiplicity M, then minus lambda is an eigenvalue of A with multiplicity M. So I haven't talked about multiplicities, as you know from linear algebra, there's geometric multiplicity, algebraic multiplicity. Here, because everything is symmetric, they are the same. So here, yeah. So that's what I mean by the spectrum being symmetric with respect to 0. Now, there are two converses to this theorem. So the first one is just you do the converse from here, okay, like just the other way around. If the spectrum of A to 0, then gamma is bipartite. I assume everybody knows what bipartite is, but I'll give the definition in a second. Now, third is actually the stronger result of a converse, but it only applies if the graph is connected. So if gamma is connected with eigenvalues lambda 1 greater or equal to lambda n, and so in the case that gamma is connected, to guarantee bipartite, I don't need this strong hypothesis that all the spectrum is symmetric with respect to 0. I just need the condition about lambda 1 and lambda n. So earlier, what did we saw? We saw that lambda 1 beats lambda n in absolute value, so it's going to be greater or equal than minus lambda n. Well, if gamma is connected with eigenvalue this, and lambda 1 equals minus lambda n, or you can say it the other way, lambda n equals minus lambda 1, or lambda n equals minus lambda 1, then gamma is bipartite. But you see, you have to be careful when you apply these results, because here, gamma is anything. Here for 3, you need to use this. It's correct. So again, let me recap. So you have a graph, gamma, with adjacency matrix A. If the graph is bipartite, then the spectrum of A is symmetric with respect to 0. What you see on the positive side, you're going to see on the negative side with exactly the same. Obviously, the negative of 0 is 0, so over there you see something. Doesn't mean that multiplicity of 0 has to be even. It can be any number. Now, conversely, if the spectrum is symmetric with respect to 0, then the graph is bipartite. And if you apply this to graph connected with these eigenvalues, then you only need to look at this. You don't need to check the whole spectrum. If these two are negative of each other, then gamma is bipartite. Okay. So again, this is a lucky. I mean, it's a lucky occurrence where you see this, in some sense, equivalence between the combinatorial property and something about linear algebra about the matrices. So let's go over the proof. Okay. Okay. So let me tell you first. Okay. Definition. What do I mean by bipartite? So just to avoid like trivialities, bipartite will have a graph that has at least one edge. Okay. Empty graph. Yeah. If is bipartite if gamma has at least one edge, and there is a partition of V equals S T such that any edge of V has one endpoint in S and another endpoint in T. Okay, so the picture will be like you have I don't know, something like this. So you have two subsets of the vertex set. These are all your vertices, and no edges inside S, no edges inside T is bipartite. And so you have this characterization, combinatorial characterization. So proposition. A graph is bipartite if and only if it has no odd cycles. So if you want to check bipartiteness, that's very easy. You can do like this search, this traversal of the graph called breadth first search, and you can check that you have no odd cycles. So you kind of, you start at the vertex, you list the neighbors, and then do I have any edges here? If you have an edge here, you have a triangle, you're not bipartite. So okay, but if If you don't have any edges, you continue. You look at the different thing. If you see an edge here, that means you're going to have an odd cycle or odd 5 cycle, and you're not bipartite. And you continue like this until you traverse the whole graph, and then depending on your answer, you decide if your graph is bipartite or not. You need like this. You need these kind of neighborhoods to be all empty in order to be bipartite. Make sense? Yeah. Now, again, the reason why people like many problems in graph theory are hard. So chromatic number, independence number, all this stuff. Some of these many questions when you look at them at bipartite graphs, you have like you're lucky. They're easier to solve in that case. So bipartite graphs are easy, and they're also the same graphs where the chromatic number of the graph is 2. You can color the vertices with 2 colors, such that you give these vertices one color, these vertices one color. Every edge has different colors on the endpoints. Okay. Okay, so let me erase here. Okay, so proof 1. Now, let's take a gamma. Let gamma be a bipartite graph. Now, I don't know, depending on which book you read, S and T here sometimes are called partite sets, or sometimes are called color classes. And this is just for bipartite graphs, because color classes, like I said, is because you can color here with one color here with the second color. A bipartite graph, it's a specific case of a multipartite graph in which you have more parts, so that's why it's called partite sets. So a bipartite graph with partite sets S and T. So this is your graph S and T here. And now we haven't gone to it, but we're going to talk about it in the tutorial. In the definition I gave of adjacency matrix, I call it the adjacency matrix. And I said you have a label, you start with the vertex set, and you have these vertices in V, and I label them 1, 2, 3, 4. Obviously, you can ask yourself, well, what happens if I don't like 1, 2, 3, 4, the ordering, and I want to do 4, 3, 2, 1, or any other ordering? That is an adjacency matrix. So you have as many adjacency matrices as you're going to have possible ordering of your vertices, and you will have different adjacency matrices. They will look different than the one that I have. But we'll see in the afternoon in the tutorials, all these adjacency matrices will be similar to each other by a permutation matrix. So all of them will have the same eigenvalues. So when you talk about eigenvalues, I can just say I take one ordering of the vertices, and I will pick the adjacency matrix corresponding to the ordering, because it helps me in a certain way. So that's what I'm going to do here, because I want to do an ordering of the like a way of adjacency matrix. So I will have a way to label the vertices of the adjacency matrix such that A of gamma is the following. So I want to put first the vertices in S, followed by the vertices in T. Okay, and the reason I do that is because in S, I know what happens. In S, there are no edges. So here I will have a 0. And let's just say cardinality of S is S. So this is 0S. This is the S by S 0 matrix. And here I will have another 0, which is 0 by T, where cardinality of T is T. Now you can ask yourself, okay, what are you going to have here? Something. Okay, how do you want to call it? Hmm? B. Why not? B. If B is here, what is here? Very good. Is B square or not square? S cross T. It may not be square. It may not be square. We don't care. Okay, so that's how it looks like. Okay, so now let's see what happens if lambda is an eigenvalue. So let's take lambda positive. Then we're going to have A times some vector U. It's going to be lambda times some vector U. Okay. Now U is as big as the matrix, and the matrix already we see that is kind of split into these blocks. So that makes it clear for us that we should split our U. We look at our vector U as something V on the first part, something W here. These are the first S entries. These are the T entries. So you kind of go a bit more into this equation based on the way your matrix looks like. So it makes sense to write it like this with V and W. And so then let's write this. We will have, let me write it here. So we have A U equals lambda U. A is of this form, 0S, 0T, B, B transpose is going to meet V and W, and is going to equal lambda V and W. So you have it like this. So this equation is going to be equivalent to what? And now you go in and you do the calculation. 0SP meets VW, so you get BW is going to equal lambda V. And the second one, B transpose V will equal lambda W. So everything in here is in here. I just did calculation. All right. And now you pick at what do I want to show? If I have an eigenvalue, I can have a negative eigenvalue. So you try to, I have one eigenvector. Now I can try to guess an eigenvector for minus lambda. Okay. I'm going to erase here. So define, what do we have? We have U, V, W. Okay, what's a good name for a vector? After you use U, V, W, what are you going to use for a vector? Huh? We use X for vertices. Let's call it U1. And no, not U1. UN. Define UN because it's for the small. Not UN. U prime. No, because it's U prime. Define U prime in Rn. U prime is, I keep the V from the top, I take the negative W here. Okay. So now, one more thing. Okay. AU is lambda U. U has to be non-zero. So if U is non-zero, what can I say about V and W? At least one of them is non-zero. But then you go, then, okay, lambda is positive. Let me see, how do we get, okay, for now I don't need, so at least one of them is non-zero. So it implies V non-zero or W non-zero. So because of that, this vector is guaranteed to not to be 0. Okay, and then you hope something works. Okay, when you multiply, so you have a u prime 0s0t b b transpose, and you multiply by v hat minus w hat, and what are we going to get? 0s here is going to be minus bwv. B transpose here is going to be B transpose V. How much was BW? Was lambda V? Minus lambda V now. Thank you. V transpose V is lambda W. And now we started with V minus. Here we have minus plus. So you put minus lambda V hat minus V hat. So that proves that this is not 0. This equation proves that minus lambda is eigenvalue. So that's very, very nice. But I have something more there. I have a stuff about multiplicity. So it's not just, okay, for sure lambda is an eigenvalue, minus lambda is an eigenvalue, but now why is minus lambda have the same multiplicity? So where are we? Yes. But exercises. Exercise 9, okay. Let's say I have, I'll use, so what, okay, I have V1, W1, I have VM, WM. Let's say this is a basis for the eigenspace of lambda. Let me just call it E lambda, or let's say fancy E lambda. So you know fancy E lambda? LaTeX, math, backslash, math cal. Okay, so backslash math cal of lambda. So if this is a basis, what I want you to show is that V1 minus W1, Vm minus Wm are going to be linearly independent. At the end, they're going to be a basis, but for now, in the first step, just prove that they're linearly independent. I mean, here, it's not about basis, it's about linearly independent. Because these vectors are linearly independent, show that these vectors are linearly independent. And so how is that going to help me with multiplicity? So I'll just say this and then we finish. If this is a basis, M is the multiplicity of lambda. If we prove this exercise, this is going to be linearly independent, and these are eigenvectors for minus lambda. So this guarantees that multiplicity of minus lambda is at least M, okay? But then you can play the same game backwards with minus lambda and lambda, so you get that the multiplicity are the same. But this is what you need here to prove that from this linearly independent, these are also linear. I mean, at the end, like I said, these bases, this imply basis, but for now, just linearly independent. Okay, we'll stop here. Thank you. Okay. So, oh, okay. So welcome back, everyone. I hope you had a good break. So we are here trying to prove this result, connecting the combinatorial property of a graph being bipartite to the eigenvalues properties of the spectral properties of the adjacency matrix. And so I left you with some exercise that will complete the proof of part one. So there was a question about, we can talk later on in the tutorial about what happens if lambda is 0, if this gives anything, but we can discuss it later. Now let's look at proof 2 and 3, okay? So for the proof of 2, I will use a result that I already used, but I'll state it now more formally. So I will use this fact, proposition, that if we are under the same hypothesis that G is a graph with, gamma is a graph with adjacency matrix A, then the powers of the matrix tell you something about the number of walks in the graph. So you're probably familiar with this. So for any L natural number and any xy vertices, if you take the adjacency matrix and you raise it to the power L and you look at the entry xy, this equals the number of walks of length L from x to y. Okay, and if you want to add it to the exercises, proof, exercise 10. So prove this. You can use. I'll give you. You can use induction on L to do this. So you take the adjacency matrix. You see, like L is 1. That's the adjacency matrix. A walk of length 1. It's the same thing as an edge. So that's clear from the definition. And then you can use, like I said, induction on L to show that this result. Okay, if you have a walk of length L from x to y, this is going to be composed of a walk of length L minus 1 from x to some vertex z and an edge from z to y. That's essentially it. Okay, so now let's prove the second part. So 2, assume that gamma is a graph such that the spectrum of A is symmetric with respect to 0. Okay, so I will use a slightly different notation now. So let me put them side by side so that you. So the usual notation I use when I don't care about. So this is the spectrum of A, and here I can repeat eigenvalues. That's why I put greater or equal to. Okay. Now, if you want to look at the distinct eigenvalues, then I will use a notation more like theta 1 strictly greater than theta 2, strictly greater than, say, than theta t, and then each of them comes with some. So you'll have here, these will be the distinct eigenvalues, and this will be their multiplicities. So it's just a different notation, because if I want to refer to distinct eigenvalues, I'll use the thetas. If I want to refer the whole spectrum, ignoring the repeated eigenvalues, I'll just do lambda. Okay. So let me give you some example. If I have the complete graph K4, then maybe you have 3 greater or equal to -1, greater or equal to -1, greater or equal to -1. So this is lambda 1, this is lambda 2, this is lambda 3, this is lambda 4. So this one or all equal. If I use the notation, it's just more condensed. You have 3 bigger than -1, and this is multiplicity 1, this is multiplicity 3. So this will be multiplicity 1, multiplicity 2. This will be theta 1, and this will be theta 2, or something. Make sense? It's just a different way of representing the same thing. Okay? Now, I probably don't need it for this part that I will do here, but anyway, I thought I'll introduce it now. Now, for this proof, the key thing is if the spectrum is symmetric with respect to 0, then what happens? Well, in that situation, if I look at, I'll use the thetas. So because the spectrum of A is symmetric with respect to 0, then if, let's say, theta j is bigger than 0, the multiplicity and let's say, and the multiplicity of theta j is, let's say, mj, then the multiplicity of minus theta j is also mj. It's the same thing as before, but just stated in terms of theta j. Okay. And now, what this is helpful? Well, it's what's gonna give us is gonna give us the following. Let's take L natural number or 0. We look at we are gonna look at the trace of a to the power 2l plus 1. We're gonna look at trace of odd powers, and we're gonna look at it in 2 ways. So one way looking at the trace is by eigenvalues. So this is going to be, I already informally here, the sum of eigenvalues. So it's going to be the sum over all j equals 1 to t of, well, let me do it with the lambdas first. The summation from I equals 1 to n lambda I to the power 2l plus 1. And then if you write it with the thetas, it's going to be the summation over j, some j. You will have theta j comes with multiplicity mj, so you'll have something like mj theta j to the power 2l plus 1. But minus theta j, so minus theta j will be an eigenvalue of a. So when you raise a to the power 2l plus 1, minus theta j to the power 2l plus 1 will also be an eigenvalue, and you will have the same multiplicity, so plus mj this. Okay, so this is just a way to show you that in this situation, when spectrum is symmetric with respect to 0, if you look at the odd powers of the eigenvalues, you add them up, is going to be 0. That's the whole thing. Okay, so you have trace is this, which is this, and obviously odd powers, they cancel out here, and you will get that this is 0. Now, On the other hand, trace of A of 2 to the L plus 1, you can interpret it combinatorially, and this is a summation over all x in V of A to the 2L plus 1 in the position XX. It's the sum of the entries of the diagonal of the matrix A to the 2L plus 1. But what I just gave you the proposition. What do you count here? Yeah, so it's the total number, is the number of closed walks of length 2L plus 1. So this condition about the spectrum, if you go via the trace, it guarantees that the number of closed walks of odd length is going to be 0 for any odd length. So it means you have no odd closed walks. And if you have no odd closed walks, you're not going to have any odd cycles, and your graph is bipartite. That's all. That's all it is here. So I won't write that, but it should be clear for everyone. Okay. So that's the second part. Now there is a little bit of an equivalent characterization. Let me erase it here. I don't know how useful it is, but you can rephrase this condition about being bipartite and spectrum symmetric with respect to 0. You can rephrase it in terms of the coefficients of the characteristic polynomial, on how the characteristic polynomial looks like. So you'll hear more about coefficients of characteristic polynomials from Professor Kanan. I'm not gonna do that here. So this result, so 1 and 2 are equivalent. What I meant to say is that there is an equivalent characterization in terms of the characteristic polynomial of the adjacency matrix of this graph as being some power of x times some polynomial in x squared. But I'll leave it here for now. Yeah.
What's closed walk mostly?
Number of closed. Oh, what is a closed walk?
Why saying closed walk, but a to the power n have the.
It's walk. Yeah, but here it's xx. So it starts at x. So the thing about, you remember, like the thing about walks, like if I have let's say a triangle 1 2 3, I can do 1 2 3 1. It's clear, yeah. So that's, but just to kind of clarify here, like when you count walks, it's kind of like looking at words. So you kind of compare the word, how it looks like, even though morally it's the same walk. So for example here, 1 2 3 1, it's a closed walk of length 3. You can have the walk 2, let me go counterclockwise, 2 1 3 1 2. These are considered different walks. So here you count all of them. So you count all of them and you get 0. Okay. Okay, so that's that. Now let's go to 3, because 3 is the more interesting part. So in 3, so you have to be careful about 3. So we have what? Assume you have a connected graph. So we want to prove that gamma is bipartite if and only if this thing happens. Lambda 1 equals minus lambda n, or something. Okay, so one implication is obvious. So from here to here, it's already done. If it's bipartite, we proved here that everything is symmetric, including the largest and smallest eigenvalues. So you're done. The harder part is to go this way. Okay. Now the only thing different from what we did before is that in this situation we assume the graph is connected, and this is a question to. I don't know if this. I don't think this works without the graph being connected. So the graph is connected. So what do we have? So assume that gamma is connected and lambda n equals minus lambda 1. So you don't have the whole information that the whole spectrum is symmetric with respect to 0. Because like in 2. In 2 you have that information, you go to the walks and you're done. Now you only know the smallest eigenvalues there, you don't know what happens in between. Of course, if you find a way to prove 2, then you're done, but you might as well just go for 1 and so on. So what's going to happen? Now, again, I try to point to you that sometimes the hypothesis, I mean, not sometimes, the hypotheses are important in mathematics, so you have to pay attention. And for this part about what we're doing here, when you see connected, it should kind of tell you something about Perron-Frobenius. There's something I need to use about Perron-Frobenius, about the graph being connected. It has to come into play in a certain way. So, let's say from Perron-Frobenius theorem, we have AU equals lambda 1 U1 for some U1 in real, and U1, let's say we can take it positive, and if you want, you can even take U1 of length 1. Okay. Now this is the thing that we have to use somehow. So we have to go after lambda n, say something about lambda n. Now, what do we know about lambda n? Lambda n is an eigenvalue. Also, let's call this vector un equals lambda n un for some un in Rn, let's say un again non-zero, un of length 1. Now the graph is connected, lambda 1 is bigger than lambda n, they're different. So what thing you know for sure about u1 and un? I didn't prove it, but it may come a bit late. Like if you have eigenvectors corresponding to different eigenvalues, I mean, we took them at the end, it doesn't matter, but so u1 and un are orthogonal, yeah. So, but u1 is all positive. So, because u1 and un are orthogonal, what can we say about un? Un and u1 is positive, un has positive and negative entries. Okay. And now we're going to write un. How do you want to write un? Un, we write un as follows. So without loss of generality, assume that un looks like this. I'm going to have a v1 on some components, v2 and some components. Okay. So basically I collect here the positive entries, and here I collect whatever is left. Okay. So this is in Rn, where v1, let's say, belongs to some rk, v2 belongs to Rn minus k. Well, I will change the notation. I'll make this minus v2. So v1 is positive. So entry-wise, let me put it as vectors. Vectors, vectors, vectors. Okay. So v1 is positive, and v2 is greater or equal to 0. Okay. So you can write it like this. And now what do we have? We have that lambda, we have that A times this V1 minus V2 will equal, my eigenvalue is lambda n, but it's the same thing as minus lambda 1. So I'll put it here. Okay, I'll put it lambda n first. V1 hat, V2 hat, minus V2 hat. And here it's going to be minus lambda 1, V1 hat, minus V2 hat. So this is because of my hypothesis. Lambda 1 is minus lambda 1. Isn't it? Now, because I have this multiplication here with this kind of block vector, I can think of A being partitioned according to the partition of V1 and V2. So if V1 is dimension k and V2 is dimension n minus k, B is going to be the first k by k, and this is going to be the remaining n minus k, n minus k. So if you want kind of an idea, okay, what is the guiding idea here? You want to show that your graph is bipartite. You want to go after you want to find a partition of the vertex set such that the matrix is going to be 0, something, transpose of something, another 0. So our goal now is to try to get rid of the B and the E and try to prove that B and E. If we can prove, so clearly C and D are going to be the transpose of each other, but just leave it like that for now. And if I can prove that B and E are 0, then the adjacency matrix will be a block of 0, something, this will be has to be transpose of something, and this has to be 0. Okay? So for now, you kind of do some algebra and you expand this. So if you do the calculation here, I'll start from the right. You get minus lambda 1 V1 equals B, so this is minus, sorry, is BV1 minus CV2. And then the other one is going to be lambda 2 V2 is going to be D V1 minus EV2. Lambda 1, thank you, thank you. Okay. Good. Okay, so that's one thing. The other thing is we can get our hands on lambda minus lambda 1 from here. Remember, like this vector v1, v2 is unit, and if I want to get just this number, I can multiply to the left by the transpose of this vector, like this really thing quick business, quotient business. So we multiply from this equation here, I multiply to the left by v1 transpose minus v2 transpose times this matrix B, C, D, E, minus V2. Here it's going to be from the left V1 transpose minus V2 transpose minus lambda 1. And this with this gives me 1, so it's minus lambda 1. Okay. And now there's some algebra, but you kind of have to do it. I'm sorry. It's for an afternoon. We have to do some algebra. It's V1 transpose minus V2 transpose meets, what do I have here? B V1 minus CV2, D V1 minus EV2 equals minus lambda 1. And one more, this is transpose, this is transpose, this is transpose. So it will be V1 transpose BV1 minus V1 transpose C V2. So I take this, I multiply here, and now I have to take this minus V2 transpose D V1 plus V2 transpose E V2 minus lambda. I hope I didn't make any mistakes. Okay. Okay. So the last one for now, I want to get to lambda 1, so I just change the sign. So I'll get lambda 1 here, and I just change the sign, so it's minus V1 transpose B V1 plus V1 transpose C V2 plus V2 transpose D V1 plus V2 transpose E V2. Okay. So you get, after all this work, you end up with something like this. Okay, question?
The last one should be minus V2 transpose.
Yes, thank you, thank you. Thank you. Okay. All right, but there's one thing that we haven't used. We haven't used lambda 1 is the largest eigenvalue. So let me erase here. So again, remember, like we started with this vector v for lambda n, which has this partition v1 minus v2. Okay. So now what we're going to do is we're going to do something. We will say lambda 1. Remember, lambda 1 is the max of all W transpose A W over all W of length 1. He beats everybody. Okay. So I will take a vector. This vector v1 minus v2 has length 1, but this is the vector of lambda n, so I won't get anything from it. But I will take the vector v1 v2, which also has length 1. So again, this vector, you see, so v1 minus v2, this is the one for lambda n. Now, if I take the vector v1 v2, this is, I don't know if this is an eigenvector for lambda 1. I don't know and I don't care, but for sure I know that this one has length 1 because the length of this vector, it's the same as the length of this vector, and I picked this to be length 1. And from this characterization of lambda 1, I know for sure that lambda is going to beat what? Is going to beat this transpose A v1 v2. So now we just have to do the calculation. So lambda 1 is going to be greater than, we've already done the calculation, so let's just do it again. So this one comes with a transpose. It will be easier now because everything is with plus. And now you don't need to worry about, it's, I think it's going to be something like this. V1 transpose B V1 plus V1 transpose C V2 plus V2 transpose D, let me see, dV1 plus V2 transpose E V2. Okay, so now look at this and look at this. What do you see in common? You see a lambda 1 here. Lambda 1 actually equals this. And you see a couple of terms in common. So the diagonal, the diagonal terms, well, not the diagonal, the other one. This is a minus, sorry. This is a minus, the off-diagonal one. So this one and this one are in both. This one has them with negative. So if I look at this expression and I look at that expression on the left-hand side, which one is bigger? this one here. So this is greater or equal than minus V1 transpose B V1 plus V1 transpose C V2 plus V2 transpose D V1 minus V2 transpose E V2. And from the calculation, so I got this calculation from the hypothesis lambda n is minus lambda 1. I know that this equals lambda 1. Okay, lambda 1 greater or equal than this. Greater. Why do you have greater or equal here? Because V1, V2 are positive, and the matrix B and C are non-negative. So clearly this beats this. It's good. So lambda 1 greater or equal to lambda 1. Therefore, equality everywhere. How can you have equality? Okay, I must have equality here. I'll leave that alone for now. I don't know, I'll get something. Essentially, this will be an eigenvector for lambda 1, but I don't care. But you have equality here. So if you have equality here, what must happen? This thing has to equal this thing, and this thing has to equal, so this and this, and this and this. Because these are the two terms that are different, so they have to be equal. So how can they be equal? The matrix B, because again, what you're using? You're using that V1 is positive. So what happens is that this B and the E have to be 0, and they disappear here, and you're bipolar. Okay, so this is one proof of this fact. There is another proof where you can look at the powers of the adjacency matrix, but that proof uses the real Perron-Frobenius theorem for matrices and so on, for irreducible matrices. So I'm not going to do that here, but this is the proof that you can do. So I was talking to some of you during the break. You have to be careful, because it's easy to, like we're always kind of tempted to get the, like a one quick characterization for a certain property. So a bipartite spectrum symmetric to respect to 0. And then you remember, okay, if the largest eigenvalue, if the smallest eigenvalue equals the negative of the largest eigenvalue, then the graph is also bipartite. But you have to remember the hypothesis of being connected. So if somebody tells you, I have a graph that has largest eigenvalue 3 and smallest eigenvalue -3, and your friend is telling you, oh, therefore it's bipartite, you have to argue with your friend a little bit. You know what I mean? We all have to do that sometimes. So you need to be connected for that part. So tomorrow I will show you another example when we talk about interlacing. When we talk about Cauchy interlacing, there is a place where we'll talk about eigenvalues of a subgraph induce eigenvalues of the big graph. Interlace the eigenvalues of the big graph. But it's always eigenvalues of an induced subgraph interlace the eigenvalues of the big graph. So the subgraph has to be induced. So you have to pay attention to this to these details a little bit. Okay. All right. So this is the proof. Any questions? No. Okay. Let me see if I had anything else to show them. I didn't, so we can do some exercises, maybe, or yeah. I don't know the count. What exercise are we? Yes, you have a question?
So that C equals to D transpose.
No, because C equals to D transpose, you get it automatically. Because when you start with your adjacency matrix, because you have this partition of V1, V2, you say, okay, I'm going to call this block B, this is C, this is D, this is E. So this is K by K. And now what do you know about A? Symmetric. So because it's symmetric, C and D are transposed. Like I didn't, I didn't bother to call, I should have called this C transpose, but transpose is going to mess it up. So B, C, D, it's a bit easier. Okay. Thank you. Yeah. Good. Okay.
So if you
Yeah, you have a question? Yeah.
I know some different proof. It's relatively easier than this. Maybe
Yeah, you can show like Professor Karan can show you a proof.
not my proof.
Do you need a microphone?
No, it's okay.
No, he has microphone.
It contains some mistakes. Please be careful about it. So lambda. So if un is the least eigenvector corresponding to the least eigenvalue, then we have this. So you define now, you consider this absolute value vector. So this I can drop. Right. So this is the Rayleigh quotient of this vector. Okay. So lambda 1 is the largest one. So this should be less than or equal to lambda 1. By hypothesis, we have lambda 1 equal to absolute value of lambda n. So everywhere you should have equality. And in one of the exercises you have, if lambda 1 is equal to this thing, then that should be the eigenvector corresponding to lambda 1. Yeah. So, okay, so you have a now un is orthogonal to the parent vector. So it should have both the positive and negative entries, or otherwise lambda n is strictly negative since G is connected. A is a non-negative matrix, so un should have both positive and negative entries. Okay, so here you have equality, so that means that everywhere you should have inequality. From here to here equality, when you will get all terms should be the same size, same sign. Okay, so that means that un into unx into uny should have same sign. Same sign, or every term inside should have negative. Okay, same sign, negative. From here to here, if I should have equality, then un into unx into uny, they should have the same sign. This product should have the same sign. That means negative, because un already has one positive and one negative entry. Okay, so that means that everything should be negative here. So whenever I have an edge x between x and y, one end should be positive, the other end should be negative. That gives you the bipartition. So collect V1, this is set of all x such that u1x is strictly greater than 0, and V2 is set of all x such that y such that u and y is strictly less than 0. Okay, if you almost have y, un should contain only positive and negative entries. It may contain 0. That cannot be, because absolute value of un, this is giving you the parent vector. The parent vector should consist of all positive entries. So this is okay. So V1, V2 gives you the bipartition. A parent vector is the eigenvector corresponding to the largest eigenvalue. This is
So where you connectedness, connectedness where we are using?
So existence of this positive vector, the third point in the morning service lecture, you have a positive eigenvector which has multiplicity equal to 1. Okay. Is it clear?
So his argument shows that absolute value of un is an eigenvector for lambda 1.
See, this is a set of real numbers and this is a set of real numbers. So I'm taking the absolute value, I'm claiming that I'm getting equality here. So when we'll get equality?
Same
No, inside the sum, whatever you have, everything should have same sign.
connectedness we are using.
Everything should be negative or everything should be positive. When everything will be, everything cannot be positive because the vector un is orthogonal to un. Or in other words, or easily, lambda n is strictly less than 0. We are considering this part. Un transpose A un. A is a non-negative matrix, 0, 1 matrix. So if every entry of un is non-negative, then you are going to get lambda n as a non-negative quantity. That's not the case. So un should have negative entries. Okay, that forces that whatever the same sign we are expecting, the sign should be negative. That is, whenever unx is positive, uny should be negative.
You guarantee that the smallest
Okay, so
the eigenvector
collect
perpendicular on
the vertices x and y according to their sign. That will give you the y partition.
but the eigenvector
So whenever you have an edge, one end should be in v1, the other end should be in v2, and you can't have an edge from v1 to itself, because if you have an edge from v1 to itself,
is an eigenvector where
that
all the
x
entries
u
are the same
into
sign.
unx into uny corresponding to that one, you will get
I
positive.
took an eigenvector for lambda n, which is perpendicular to that. And
The idea morning Sebi explained,
the first
just only the last part we can.
it means that the one of lambda n has to have positive and has to have some.
Any doubt?
So that's why I could partition into v1, v2.
This is not my idea. Yeah, I found it in some place when I was teaching this course. I gave this proof.
Huh?
Connected.
No, it's because of Ferron-Frobenius.
Parent
Because the graph is connected, it implies that u1 is positive, therefore u1 and perpendicular to it is going to have positive and non-positive entries.
Okay.
So we are just using the fact of Ferron-Frobenius.
Yeah, just the fact that you have a positive eigenvector for the first eigenvalue.
That I am understanding, but I am not able to see that connectedness of the graph.
So you get positive eigenvector from the connectivity
Okay,
of the graph in Ferron-Frobenius. Yeah. Okay. Oh, sorry.
Okay. Now,
Okay.
some volunteers for start solving more.
So I understood there should either be both positive or both negative whenever there is an.
Yes.
And then we conclude this is a bipartition.
See, what sum says, whenever I have an edge
Yeah.
between x and y, at that time only I will have some non-zero terms here.
Yeah.
Okay. So if we have an edge from v1 to itself, then that means that both ends are having positive.
Okay. Yeah, when you define this, you can observe that this is a
Simple positive. Yes. Okay, so maybe you can volunteer by solving problems one by one. The initial problems are easy.
Oh, maybe do I have to call on people?
Yes, sure.
Oh. Yeah, we have 15 minutes or 10 minutes, 20 minutes. Okay. I lost track of exercises. Anybody remember? Oh, no.
Typing is typing.
Oh, okay.
Some of them are already.
Oh, okay. Okay, so let's do the exercise question 10. You have this thing with the bipartite, so it looks like this. And we said something that if you have
I mean, you have these vectors u1, v1. So this was the first part. I mean, this, and how did we, what was the argument here? Where were we using this? This was a basis for, remember, fancy E lambda. And we proved that this is, these are eigenvectors of minus lambda. So if we prove A, we get that the multiplicity of lambda, we get the multiplicity of minus lambda is going to be greater or equal than multiplicity of lambda. Because multiplicity of lambda, we take m, and I have a basis here, and it's linearly independent, then it guarantees that these things are going, because these ones, we already proved that they are eigenvectors for minus lambda. So once you prove multiplicity minus lambda is bigger than lambda, you can do the same argument for minus lambda and lambda, and you get that they're equal. Okay? So clearly A implies B, but A requires, is it obvious? So I'll let you think for 2 minutes. I'll erase the board, and then somebody can come and write down a proof. I told them 2 minutes, so okay. Give them 2 minutes. Can you guys see from here over there?
Yes.
Huh? Okay.
if someone likes your presentation, they make you job immediately.
Yes. Okay, I don't know what to do. Should I keep asking them, or are they, or should I talk about something else? We'll leave it.
Nobody got the answer?
Okay, do you want to go write it down for everybody? Come on, it's okay.
Some of them they both.
Yeah.
We can assume it as LD, then it could be like alpha 1 and alpha x1. So from here it will be alpha 1. From this. This will be alpha 1. So if it is LD, then at least one of them must be LD. This one or that one. Okay. So if any one of them is LD, so the okay. So this is the line. So from here it could be alpha 1 u1, alpha u1, alpha 1 u1, alpha 1 u1. This implies alpha is need to be equal to so if it is Li, means if we take any linear combination of these vectors, then all alpha must be equal to. But I'm taking here it as LD, and if it is LD, then it means this or this alpha is must be non-zero. So from here alpha I must be 0, and here we are getting alpha is non-zero. Contradiction.
Any questions? Clear? So I think you're proving the contrapositive. Just linear dependent implies linear dependent. Yeah.
So if it is LD, then it should also.
Yeah. And yeah, this is useful because it gives you a recipe. If you know some eigenvectors for an eigenvalue for bipartite graphs, you can get the other ones just by changing the sign. Yeah. Very good. Okay. All right. Thank you. Okay. Very good. Go to the Okay, so I was looking at the schedule, so we're supposed to do in lecture 2, I guess I didn't have time, Rayleigh quotient, max min theorem, and so on, and so maybe I'll do that now.
The break shall we do?
Will you do break now? Oh yeah, let's do break and then I'll do this. Okay, we'll take a break now.
Maybe some side problems you can do. Calculating eigenvalues of complete graph. Calculating somehow.
Yeah, I gave them the. Did anybody do the orthonormal basis of Kn? Or okay, so where are we with exercises? Number 11. Okay. Exercise 11. Okay, before I give you exercise 11, let's do some, okay, so complete graph, Kn, adjacency matrix of Kn is Jn minus In. Eigenvalues, I'll give you another n minus 1 with, I'll put it multiplicities as exponents, 1, and minus 1 with multiplicity n minus 1. So this is the same kind of notation as before, but multiplicity as exponents. The second one, complete graph KAB, complete bipartite KAB, adjacency matrix of KAB is 0A, all 1AB, all 1BA, 0B, and then find eigenvalues, square root of AB with multiplicity 1, 0 with multiplicity L plus B, A plus B minus 2, and minus square root of AB with multiplicity 1. Okay, so I haven't done the proofs of this, but you should know how to do it. If somebody, asks you how to calculate, this one is pretty straightforward. This one is a little bit of work, but it's not complicated. So here again, find for Kn and KAB. Let's see how, if you want to do it by hand, how complicated it is. So you can have fun with it. Then we can wait. If you want, we can take a break now.
Yep.
Yeah. Okay.
Check with the coffee.
Yeah. Yeah. Okay, so for the last hour, I'll just do two things. So one is graph theoretic, and one is about linear algebra that I will need tomorrow when we talk about eigenvalue interlacing and equitable partitions. Now, one thing I didn't mention, but one way, if you know, I think Godzilla and Royal in their book, they talk about this. Maybe other books talk about it as well. When you want to think about an eigenvector of graphs, so if you have, let's say again, gamma VE, and you have a adjacency matrix of gamma, and you want to maybe you're looking for an eigenvector, or you're looking for an eigenvalue. How do you think of it in terms of the graphs? If the graphs are fairly small, this equation, you can think of it in terms of picture, in terms of and the idea is that you look at this equation entry-wise, and entry-wise, again, let me change the order. It means that for every vertex in the graph, lambda times ux, it's the sum over all y adjacent to x of uy. Okay? So if I'm looking, I'm looking for, again, something very simple. I'm looking for the graph, complete graph. Let's say I don't know what it is. I'm looking for some kind of labeling of the vertices u1, u2, u3, u4, u5, such that when I pick any vertex and I sum up the entries on the neighbors and I divide by the value here, I always get the same number. And that will be the eigenvalue eigenvector. So in this case, I mean, I'm cheating a little bit because you all know, like, I can put 1, 1, 1, and the entry here is 1. What are the neighbors? The neighbors are 4, so the sum of the neighbors is 4. You're dividing by this entry here 1, you get eigenvalue 4. Okay? So that's one way you can think. So if you encounter in your research some small graph and maybe your first impulse is, okay, I'm going to go fire up a characteristic polynomial and give me some, that can work as well. But for some small graphs, you can do something like this. And then the same graph, if I'm looking for some other eigenvalue, I can do 1 minus 1. I can do 0, 0, 0 everywhere. And we'll play with these ideas tomorrow in more general way. But okay, here, what's going to happen if I pick this entry? The sum on the neighbors is going to be 0. So my eigenvalue could be anything. Okay, so that's not helping. So pick something that is non-zero. I add up on the neighbors. I get a minus 1. Minus 1 by 1, it gives me minus 1, the eigenvalue minus 1. So this one, it will give me the eigenvalue 4. This one will give you an eigenvalue minus 1. And the advantage of doing this is that you can build yourself linearly independent vectors. Because I have 1 minus 1, 0, 0. Well, once you figure out that, you can do 1, 0, minus 1, 0, 0. And you move this, and you're going to get yourself four eigenvectors for the eigenvalue minus 1 that are going to be linearly independent. Now, granted, they're not going to be orthonormal basis. Like, this one, it's easy to normalize. These ones, you have to do a bit more work, some Gram-Schmidt and so on, but you understand what I'm saying. So I just wanted to say that because it's useful to play around with example by yourself and to do these things. And maybe sometimes you feel intimidated, but essentially for adjacency matrix, this is the entry-wise equation is the one that you have to keep in mind when you're thinking about eigenvalues, eigenvectors. Of course, if you're talking about Laplacian matrices and other matrices, this equation is going to be different. So you have to, this one is the simplest one as far as I can tell, because for Laplacian, you're going to have a degree and it's going to mess you up a little bit more. Okay, so I thought I'd say this. Now, tomorrow we're going to do some serious theorems about interlacing and equitable partitions and all that. So to do that, I'm going to need something something about max-min theorems about eigenvalues. So eigenvalues. Now, this is something when I was a student, it always intimidates me. Even now, I have to look it up to get the details. So let's go through it slowly and to understand what's going on, and then you know this will be the main topic for the rest of the. So we have again, let A be a real and symmetric matrix. With eigenvalues lambda 1, lambda 2, lambda n, and corresponding orthonormal eigenvectors u1, u2, un. So before, let me fit it here. Before, we just saw something of the form lambda 1 was the max over all u in Rn, u non-zero of u transpose au divided by u transpose u. Okay? And once you normalize, you do the same thing with norm 1, but I'm not going to. And you can, from the same proof, you can get the obvious thing that lambda n is the minimum over all u in Rn of these Rayleigh quotients. So okay, so lambda 1, lambda n. So what makes them so special? Well, lambda 1 is the largest, lambda n is the smallest. What about some ones in the middles? Can you characterize them like that? So that's what I will tell you now. So to do that, let me step aside here and kind of go through this a few things a bit slowly. So you have A, you have lambda 1. Let's say I have here some, let me go from here. Lambda 1, lambda 2. I have lambda j here. I have lambda n, and I have u1, u2, uj, u. Okay? So in some sense, so this is how you can remember what we're going to do in a second for general lambda j. So lambda 1 is going to be the largest, so it's the largest in this sequence, so it's going to be the largest of the Rayleigh quotient in the space spanned by everything, which is Rn, which is the space spanned by u1 all the way to un. Lambda n, again, because it's at the end of the spectrum, is going to be the minimum of that. Now, what I want to say something about lambda j. Okay? So for lambda j, is going to be a little bit, that's where we're going to have this max, min, max, and you always, okay, which one do I go? How do I sort it out? So for now, I will have, this is going to be capital Uj. So this will be the span of U1 all the way to Uj. So you see, like if you are in this span and you take a vector from here, and I'll write it down in a second, and you look at the Rayleigh quotient, lambda j loses because lambda j is the smallest. It's the smallest in this set. And then we're gonna I'm gonna look at a different subspace, which is gonna be like this. Let me see how I denoted my notes. Well, if this is uj, this is going to be uj minus 1 transpose. So it's the one from uj. So from uj, when you're in the middle of the pack, you can look up and you can look down. So uj is going to be here, and lambda j loses in this set, but lambda j wins in this set. Okay? So now, again, exercise, how much? 12. Exercise 12. if I take the minimum over all vectors u in uj, u non-zero, of u transpose au divided by u transpose u, what do I get? Lambda j. Okay, so that's part one. And then part two, I look this way. If I look at the maximum of, I don't know, let's say v, v transpose av, v transpose v, v transpose v, no, v transpose v in uj minus 1 transpose perp, sorry, perp v not 0, this is also going to be lambda j. Okay, so in some sense, what we saw here, it's kind of like something that is just happens for lambda 1 and lambda n, because lambda 1 can only be the maximum of everybody. Lambda n can only be the minimum of everybody. Here, lambda j, if you look from two perspectives, if you look up, lambda j is the smallest. If you look down, lambda j is the biggest. So that's kind of like, with that perspective in mind, lambda j is going to be the minimum of the Rayleigh quotient over this space, and it's going to be the maximum over this space. So this is the same proof that we did before. I'm not going to do it. Okay? Okay. So, okay, why am I telling you this? Because now we're going to write, so lambda j is already the minimum of that. Then, okay, eigenvectors. Then, 1. Lambda j is going to be the maximum over all subspaces W of Rn with dimension of W equals j of the minimum of see if I get it right. Minimum of U contained in W, U non-zero, of U transpose A. Okay, so that's one part. And I don't know if I'll fit the second part under it. So, let's try 2. Lambda j, you can write it in 2 ways, but okay, it's going to be the minimum. How do I have it? Minimum over, let's say again, W in Rn, dimension of W is j minus 1 of the maximum over U in W perp, U not 0 of this Rayleigh quotient. Okay. Which one? Dimension.
N minus j plus 1.
No, I'm fine. I think.
N minus j plus 1. Perpendicular, orthogonal.
Where are you? I don't.
Here you see.
Okay.
Uj minus 1 plus.
Okay. Yeah. But uj minus 1 is this one. uj minus 1 perp is going to be of. Is going to so uj minus 1. The dimension of uj minus 1 is j minus 1, and the dimension of this uj minus 1 perp is n minus j plus 1.
Yes.
Yeah.
So the dimension here should be n minus j plus 1.
No. I think this is okay. Well, let's go through the proof and we'll see, because so the space here w perp is going to have dimension n minus j plus 1. Okay, so yeah, you can change it from perp. You can remove the perp, but I thought it saved me some time. Okay, so let's just do one, and then I'll leave the two for you. So proof 1. Again, it's a maximum. So kind of informally, you have here the subspaces of dimension j of Rn. Uj is one of them, but there are many other subspaces. Okay. So you have this quantity which depends on W, and what you want to show is that if you take all these quantities and lambda j is going to be the largest of them. So there is a max here, and the reason it's a max and it's not going to be a supremum is here because it's going to be attained for uj. But to show this part, we have to do two things. One, we've kind of already did it, but then we have to do another thing. So one, for any W subspace of Rn with dimension of W equals J, I'm going to look at this quantity minimum of I'm going to look at this quantity, and I want to prove that if I take this minimum, lambda j always beats it. Okay? So if you are the maximum of something, you have to be greater or equal than everybody else, and you have to have some equality. You have to attain equality. The equality part is going to be attained here with uj. That's the equality part. So again, so in order to prove this statement 1, we have to do two things. This one, and there is, so I'll write it like this. There is W subspace of Rn, dimension of W equals J, such that lambda J equals the mean of U in Rn Okay. So if you're the maximum, you beat everybody else and you attain the maximum somewhere. Okay, and this part 2, it's from here. So this will give you part 2. So I won't do that, but I'll quickly go over this. Okay. Okay, for any W, so proof, what do I want to show? I want to show for any W subspace of Rn, dimension of W is J. I have that lambda J is greater or equal than minimum of V in Rn. There is V, U, sorry. Okay. Okay, so what do you have to do when you want to prove that a number is bigger than equal than a minimum of something? What is it? Not any, it's a minimum. So if I find a vector u, here, oh, this should be in W, sorry. If I find a vector u in W, which is not zero, such that lambda j beats the Rayleigh quotient of that, I'm done. Okay? So I just had to find a vector. So, so that's what we're gonna do. Okay, how do we find it? Well, this is a game of dimensions. It's a dimension argument. So what we have is because dimension of W is J, and so again, you play the you see like lambda J has plays two roles at the same time. On one hand, is the smallest if you view it from the top, lambda 1, lambda 2, lambda J, and on the other hand is the largest if you view it from its down. Okay, so that's kind of you play. So you have this. Now, what we're going to look at this uj minus 1 perp vector. We have the dimension of uj minus 1 perp. So uj minus 1 is from 1 to j minus 1, so the dimension of the perp is going to be the rest, so it's going to be n minus j plus 1. You do the usual thing. We have that. The dimension of W intersect uj minus 1 perp is what? Is the sum of the dimension minus the dimension of the plus of the okay. So now what do I have? Dimension of W is J, dimension of this is n minus j plus 1. Minus the dimension of this. But here you have minus, so what I want to, how big can the space be? W plus uj minus 1 transpose. The whole space. So this dimension is less than or equal to n. So if I take a negative, this is going to be greater or equal than j plus n minus j plus 1 minus n. And that is exactly why you took here this, because it's n minus j plus 1. And when you add up, you get more than n. So you get n plus 1 minus n is 1. Okay? So what does it mean? Non-trivial intersection. So there's a non-trivial intersection. Therefore, there is, I call it V in W intersect uj minus 1 transpose W not 0. Okay. I'm gonna I'll erase here. No, I'll leave it. You okay with this? I'll erase it. So now we look at this W transpose A W. Again, it's in the intersection, so it's going to be a double agent. Is going to play two roles for us. Okay, this what do I call it? V. I call it V. Sorry, V. V. Okay. Now, because V comes from the space W, this is going to be greater or equal than the minimum over all U in W, U transpose AU. This is because V belongs to W. And obviously V is not 0. But now the stuff that I erase, because V comes from the space uj minus 1 perp, which one is the biggest number there? Lambda j. So here, because V belongs to uj minus 1 perp, this is going to be less than or equal than lambda j. So for this max min theorem, it's always, you need to find an intermediate like this. Like I said, it's all about a double agent, like some vector that is not zero, that is going to help you on both sides. And this vector is guaranteed. That's why these dimensions are what they are and so on. This vector is guaranteed in this way because, again, W has dimension j, this space has dimension n minus j plus 1, and you're going to do this this dimension argument, and you get this this W, and that's how it works. Now for the so I think that does the proof, because this proves it proves this part 1. Lambda j is greater or equal than the minimum. So this finishes part 1. And then part 2, like I said, I left you as an exercise. You take here to, you take this U to W to be uj, and you're done. Okay. So this, like I said, it takes a bit of time. We're gonna recap it tomorrow, because tomorrow I will use this to prove these results about eigenvalue interlacing. It's how you compare the jth eigenvalue of a big matrix with the jth eigenvalue of a small matrix. And this is the tool that's used there. So I figure I give it to you today so that tomorrow you're not going to be saddled with this stuff plus the extra stuff. So this will give you a little bit of time to just think about it and try to write it down a few times and see what you can you can get out of it. Now I'm not going to go through the proof of this one, but it's going to be the same type of argument. Like for the proof of this second part, again, you break it down into two things. Some inequality, general inequality for any subspace of dimension blah blah blah, you do this, and then there is a subspace such that happen, and that subspace, again, you get it from certain like extreme eigenvectors, the ones to the left or the ones to the right. Okay. Okay. Any questions? No? Okay. All right. Okay, I'll leave this here. Let me see what I want to do now. Let's do a couple more things before we finish up. So I'll leave this here again. This is the same one I'll use tomorrow. So here are a few things. I forgot the exercise number. 13. Okay, it's the usual thing. If gamma is a graph with eigenvalues lambda 1 all the way to lambda n, again, adjacency matrix, and max degree delta and average degree d bar, then lambda 1 less than or equal to delta greater or equal than d bar. So the largest eigenvalue of a graph is always between the maximum degree and the average degree. And that's why, that's one of the reasons. This result is that sometimes when you look at questions about the number of edges in a graph and so on, the size of the graph, like extremal question, maximizing the number of edges with certain property, some people now study something, spectral versions of it, where you want to maximize the largest eigenvalue with the graph with those properties. So now for this inequality, you have two inequalities. I'll let you think about them. Maybe some of them you already know them. So maybe some of you don't. So I'll let you think for 2 minutes and then I can ask participants. Do we give them maybe more coffee or tea if they come to the board or?
More alumnus.
Oh, yeah. Well, no, because I ate all of them, so I'm sorry. No, maybe tomorrow, but yeah. So I'll give it 2 minutes. Just think about it, and then we can, if you know how to solve it, come and do it. If not, we can, and then we can do something else. Okay? So just 2 minutes. So some of them may know, some of them may not know.
Yes,
so yeah, I'll
We are trying to prove there exists some some
subspace.
some vector.
You here? Here?
The number one.
Number one. So this is so you have this W which is here and it's also here. So because it's here, you get this. By this, you'll write it as linear combination. Because it's here, this is the minimum over everything in here, but this vector is in there. So this, the minimum is less than. So there's no linear algebra here. This is just the minimum value of a function is less than or equal than the value of a function at some point. So
the first one, lambda j.
So that's what you have to do. So you have to write down, because you see v is in uj minus 1. So uj minus 1 was the span of the first. And uj minus 1. Do I get it right? No. Oh, no. Let me see. So uj perp. So here, lambda j. So lambda. But no, this should be the maximum. Did I get it wrong? Let me see.
No, it's okay because uh, yeah, but so here I'm not doing yeah. So the forget about max or mean. Here I have a vector v from here. I'm going to have a vector v from here. So this vector v is going to be a linear combination of this. So when you calculate v transpose a u v transpose v, this thing lambda j is going to be bigger than u because v comes from this set and lambda j is the biggest. So it's the same as we did lambda 1, lambda n earlier, the same type of argument. It doesn't, because you don't know anything about this v.
Yeah, but on the other side, we have minimum and then that is equal to lambda.
It doesn't have to, it's going to be for some subspaces, but it doesn't have to be for all subspaces. Because you see, like we took W to be an arbitrary subspace of dimension J. There are many. It's not going to happen then. So yeah. So try to this one, like you're going to have to write down the proof again and try to see if you can remember it without looking it up. I mean, or the best thing, try to do the proof for part 2 for this one. Try to do the proof of this one and see if you can set it up in the right way, and that's how we can do it. Okay. Any? Oh no. Okay. What is it? Average degree. So the average degree is going to be just the sum, or you take all the vertices and you sum up their degrees and you divide by the cardinality of V. So let's just do a simple example. So the graph that we did a bit earlier, this one, you have like the degrees. So I'll just write on the vertex, I will write the degree of the vertex. So here you have degree 3, 3, 2, 2. So the average degree here, you 3 plus 3 plus 2 plus 2 divided by 4 is 2.5. Okay? And the maximum degree is obviously 3 because it's the maximum degree. So this inequality says lambda 1 is between 2.5 and 3. I don't know what this lambda 1 is here. You know, that's another exercise you can try to calculate. I'll show you an easy way to calculate it tomorrow. But that's basically the result. Okay, so that's what your colleague was asking about. What is the average degree? Okay, so so let's go over the proof of this fact. I'm going to erase here. So there are two inequalities. Let's do them side by side. So let's do first lambda 1 greater or equal than the average degree. So again, because you have this formulation of lambda 1 as a maximum of this Rayleigh quotient, when you have inequalities in which lambda 1 sits on the bigger side, that could be a place where you can apply that. So yeah, you can do, that lambda 1 is going to be the maximum over all vectors u in Rn, u non-zero of u transpose au, this. So that means lambda 1 is going to be greater or equal than this for any vector you give me which is non-zero. So then the simplest vector you can think of is all ones, and you plug, you get that lambda 1 is greater or equal than the all one vector plugged in here. And you're going to get here, you're going to get the average degree. And this is
of course, you can be greedy now, and you can say, well, if I want inequalities for lambda 1, I can apply this to powers of A, I can apply it to polynomials of A, but you have to be careful so that in those polynomials of A, when you apply the polynomial lambda 1, you still are the biggest value. So people have used that, and you can get inequalities involving the power of lambda 1 and the number of walks in the graph and so on. So that's, you can get like here, you apply these inequalities to various functions of A, you get many inequalities. So I'll just show you one. Now the second part, delta greater or equal to lambda 1, here it's useful to think about this type of a view of eigenvalue, eigenvector part. So you can think of, you have AU equals lambda 1 EU1. Now, I don't have anywhere anything about connected, so I don't need to use, I cannot just say U1 is positive, but I don't need that, okay? But I have that U1 is not 0. Okay, so there's some entry which is not 0. Now, what I can do is take x in V such that U1 in the value x, let's say in absolute value, is the maximum over all y in V of U1 y in absolute value. Okay, so then, the value in the eigenvector entry at x in absolute value is bigger than everything else. Then you look, okay, what happens at the vertex x in the eigenvalue eigenvector equation? So let me, I guess we're good with this proof, so I'll erase it here. So from this equation, you have that lambda 1 u1 at x is the sum over all y adjacent to x of u1y. And you just apply absolute value to both sides, and you get lambda 1 u1x is going to be the absolute value here, so it's going to be less than or equal, by triangle inequality, summation of y adjacent to x of absolute value of u1y. But which one is the biggest value of these u1s? Right, it's the u1x. So this is going to be summation less than or equal, then the degree of x times absolute value of u1x. Because you put this over here. And then you can take your absolute value here. And now u1 is not 0. u1x is a maximum absolute value. So this is guaranteed to be positive. And now you divide. And you get something stronger than what I told you. You get lambda 1 is less than or equal than the degree of x, where x is a vertex of maximum eigenvector entry. Well, does x have the I don't know what degree it has, but I know for sure it's going to be less than or equal than the degree of d. Okay? So see if you can build a graph where the maximum eigenvector entry is not at a vertex of maximum degree. See if you can do that. Okay.
The degree of x is for all x, for any x.
For some x. Well, you see, the x, you take an x where the eigenvector entry in absolute value is the maximum. Okay. If the graph was connected, I could have taken an x where u1 the entry is the maximum. I forget about absolute value because I have all entries positive, so I don't care. But in general, you just take one where the absolute value is the largest, and then you write eigenvalue eigenvector equation. And so this eigenvalue eigenvector equation, you see that you have information locally. You have information about the vertex, the neighborhood. You can play a game. You can even look at the second neighborhood, and you can get some extra information there. And people have done that. People have, it's commonly used in some research paper to get information about that. But for now, I think that's good enough. Now, question for you: when do you have equality in this bounds? So here, equality, and why is that? If and only if, or if so when is lambda 1 equal to the Rayleigh quotient of a vector? What does it mean about that vector? It must be an eigenvector. So in that case, for this inequality, the all 1 has to be an eigenvector to lambda 1. And when you write down what it means, A1 equals lambda 1 times the all 1 vector, it means the graph is regular, okay? So, okay, here, equality, if and only if regular. What about here? Somebody said regular, I don't know who. How many people for regular? Okay, one person for regular, two people for regular. How many people to let's be more careful? What is it? One component can be a big regular delta regular graph, and then you can put a bunch of things around it that makes it not regular. So you have to be careful. So here, if in addition I gave you the hypothesis the graph is connected, then it will be regular. But for now, you cannot say. Like you can say something, a component where you have delta as an eigenvalue is going to be regular, but that's about it. So be careful about these things. Don't just jump to, just because. So you have to analyze them a little bit carefully. But you see, it's not super hard. So maybe we'll finish now. Okay. Okay, it's a bit early, but they've been good students, so they need a break. So I ate all their snacks, so they need a break. So we'll stop here. Thank you. Yeah. Okay, I think